When the object now called 3I Atlas was first noticed, it didn't look like much. Just a speck of light in the data stream, one more point among countless others, until orbital analysis revealed something that changed its classification forever. It wasn't bound to the sun. It wasn't moving along the neat ellipses that define the rest of our neighbourhood. It wasn't one of ours. The calculations showed a hyperbolic trajectory, meaning it came from beyond the reach of the solar system's gravity and would leave just as quickly. Another interstellar visitor, the third we have ever recorded following the path of Oumuamua and Borisov. Yet almost from the moment of discovery, it became clear that Atlas was different. The more information we gathered, the more the details refused to fit into the categories we had prepared. From the earliest orbital solutions, astronomers could say with confidence that it would not strike Earth, that its path was stable, that no catastrophic impact scenario was waiting in the shadows. But once the immediate danger was dismissed, the real questions began. Why this speed? Why this chemical profile? Why these inconsistencies in the data? Why did each observation answer one puzzle while creating two more? It didn't behave like a typical comet, yet it wasn't a rock either. Its light curve suggested irregularities, but nothing conclusive. Its outgassing was strange, but not unprecedented. Its trajectory was predictable, yet the history that placed it on that path remained a mystery beyond reconstruction. A visitor from nowhere, yet one that refused to tell us where it had been. When Oumuamua passed through in 2017, the mystery was concentrated in its shape and acceleration. With Borisov in 2019, the intrigue came from its more familiar cometary activity that nevertheless raised questions about its birthplace. With Atlas, the strangeness comes from accumulation rather than singular anomaly. Every detail seems almost understandable until placed beside the next, at which point the contradictions surface. Its orbit confirms interstellar origin, but the velocity is greater than expected. Its coma composition matches certain exotic scenarios, but diverges wildly from most cometary chemistry. Its brightness is measurable, but models of its nucleus size shift dramatically, depending on assumptions about reflectivity. It is, in other words, a puzzle composed entirely of pieces that don't quite interlock. Astronomers are used to working with incomplete data. Every comet, asteroid and trans-Neptunian object has gaps in the record. Yet most of the time, those gaps narrow as observations accumulate. The longer we watch, the clearer the picture becomes. With Atlas, the opposite has been true. Early measurements seemed straightforward enough. But as the campaign of observations expanded, instead of convergence there was divergence. One group emphasized its extraordinary velocity, another its unusual spectrum, another its erratic brightness variations. None of these claims were baseless, yet together they painted a portrait of an object that seemed to resist categorization more with every added line of data. Consider its velocity. Hyperbolic excess speed of 61 kilometers per second, meaning that even after escaping the gravitational pull of the Sun, it will still carry that residual pace into the galaxy. For comparison, Oumuamua travelled at 26, Borisov at 32. That makes Atlas nearly twice as fast as either of its predecessors. The simplest explanation is violent ejection from its home system, perhaps during planetary migration or stellar encounters. But if that's the case, why does each confirmed interstellar object seem faster than the one before? Is this selection bias, a coincidence, or a hint of something systematic that we haven't accounted for? Chemistry adds another complication. When the James Webb Space Telescope obtained spectra, the results pointed toward a coma dominated by carbon dioxide, with a CO2 to water ratio around 80:1. That alone would be striking because most comets in our system are water-dominated, with CO2 as a secondary volatile. To find one with so little water relative to carbon dioxide challenges models of icy body formation. Did Atlas originate in a system where the snowline for CO2 played a different role? Or has it been altered by billions of years of exposure to cosmic rays in interstellar space? Or is there something more that we're not identifying yet? Each explanation seems possible in isolation, but none align cleanly with the broader profile. Its brightness variations are another example. Photometric monitoring showed fluctuations consistent with rotation, but estimates of its rotation period vary wildly depending on how the data is modelled. Some analyses point toward rapid tumbling, others toward a stable spin with irregular activity driving changes. That wouldn't be unusual for comets, which often vent asymmetrically, but the mismatch between models leaves an uncomfortable uncertainty. A visitor we should be measuring with increasing precision instead leaves us with a widening range of possibilities. This uncertainty extends to its size. Estimates for the nucleus diameter range from a few hundred meters up to several kilometers. That's the difference between something smaller than a city block and something approaching the scale of a mountain. Normally, combining brightness with coma activity gives a reasonable constraint, but in this case the dust production efficiency and surface reflectivity cannot be pinned down with confidence. A dim surface on a large body could mimic the brightness of a smaller but more reflective one. Neither scenario fits comfortably with the gas ratios observed. The consequence is that we talk about Atlas as if we know what it is, while in fact even its most basic parameters remain stubbornly blurred. The strangeness of Atlas has not gone unnoticed by those who lean towards speculation. For every cautious explanation offered by observatories, there are voices wondering whether such anomalies might hint at artificiality. After all, Oumuamua sparked years of debate on that front, and Atlas has no shortage of peculiarities. Yet when examined carefully, the data still favours natural interpretations. The problem is not that Atlas behaves in ways that suggest it must be engineered, but that it behaves in ways that continually complicate our natural models. Each time we think we've isolated the explanation, another measurement appears that reopens the question. This is why the phrase, "a visitor from nowhere," resonates so strongly. We know its trajectory, but not its origin star. We know its chemistry, but not the conditions that created it. We know its velocity, but not the encounters that accelerated it. It arrives in our system bearing clear evidence of history we cannot reconstruct, carrying secrets in its nucleus that may never be fully unlocked. The paradox is that the more carefully we measure, the more contradictions emerge, until we begin to feel as though the act of studying deepens the mystery rather than reduces it. This makes Atlas not just an astronomical object, but a kind of mirror held up to our own limits. We are reminded that detection does not equal understanding, that discovery does not guarantee explanation. Each spectrum, each image, each calculation adds another layer of complexity that we then struggle to integrate. Our tools are more advanced than ever, our telescopes more powerful, our models more sophisticated, and yet here is a chunk of ice and dust, no larger than a mountain, that manages to evade our full comprehension. And so we continue to watch. Night after night, telescope time is allocated, data streams accumulate, analyses are published, and still the sense of certainty does not solidify. Instead, Atlas seems to play a different game, one where each answer unlocks a deeper ambiguity. We thought the challenge would be distinguishing between natural and artificial explanations. Instead, the challenge has become reconciling the natural explanations with one another. It forces us into humility, because in the end what we have is not an alien spacecraft nor a catastrophic threat, but something in many ways more difficult. A natural object whose behaviour remains just outside the reach of full understanding. The story of Atlas begins as a simple detection, a point of light flagged by software and confirmed by human review. But what began as a technical entry in a catalogue has become a source of ongoing confusion, an example of how astronomy is not simply about collecting data, but about confronting the limits of what that data can tell us. A visitor from nowhere, leaving behind not destruction, not revelation, but questions that multiply faster than answers, and as its trajectory carries it closer to perihelion and eventually back into the interstellar dark, those questions will continue to follow, reminding us that sometimes the more we study, the less we truly understand. When astronomers first plotted the orbit of 3I Atlas, the mathematics carried a comforting clarity. Orbital mechanics is a language of precision, honed through centuries of observation, and it rarely leaves room for ambiguity. The data points lined up with models that had been tested countless times against comets, asteroids, and spacecraft. The calculations confirmed without hesitation that Atlas was unbound, a hyperbolic intruder destined to cross the solar system once and then continue outward forever. The numbers gave us assurance: no risk of collision, no gravitational entanglement, no catastrophic scenario hidden within the mathematics. In that respect, the certainty was immediate, but within that comfort the first hints of trouble were already present. Certainty in trajectory does not translate into certainty in origin, nor does it explain the strange way the object's behaviour deviates from expectations. Every step that followed the orbital solution produced new measurements, and each measurement opened a fresh path of doubt. We know its path with exquisite accuracy. We can tell you where it will be on any given date with greater precision than we can predict the weather tomorrow. Yet when it comes to what it is, where it came from, and what it tells us about the broader galaxy, the details resist alignment. The object's orbital eccentricity is greater than 1, confirming its hyperbolic nature. That single number sealed its classification as interstellar, but eccentricity alone doesn't explain why its excess velocity is higher than any previous visitor. That detail stands out like a question mark in the middle of a clean equation. We can calculate the speed with confidence, but explaining why this particular body has acquired that speed drags us into a swamp of speculation. Perhaps it was ejected violently by a massive planet, perhaps accelerated by multiple stellar encounters, or perhaps the distribution of interstellar wanderers is broader than our limited sample suggests. Each possibility remains plausible, yet none are definitive. The numbers sit firmly on the page, but the story they tell branches in too many directions. When the James Webb Space Telescope turned its instruments toward Atlas, the data that returned was equally crisp in its precision. The spectra showed strong carbon dioxide lines, unmistakable and undeniable. Ratios could be measured, compared, and catalogued. The CO, 2 to water ratio of roughly 80 to 1 is not a vague impression. It's a value backed by clear, repeatable signatures. The numbers on that spectrum are not in dispute, and yet those very numbers generate doubt rather than resolve it. What formation conditions create a body so dominated by carbon dioxide? Why is water so suppressed? Could this be a matter of surface chemistry altered by cosmic rays? Or is it fundamental to the nucleus itself? The data is clear, but the interpretation fragments. Brightness offers another example. Observations from ground-based telescopes track its apparent magnitude with time, each measurement adding to light curves that are plotted and compared. Those light curves show fluctuations consistent with rotation, the mathematics of periodic variation easily extracted. Yet once again, the clarity in measurement feeds uncertainty in interpretation. If the fluctuations result from rotation, why do models produce such divergent rotation periods? If the changes come from activity, why are the gas and dust outputs inconsistent with the magnitude shifts? Certainty in the light curves leads directly into doubt about the physical cause. Even size, one of the most fundamental properties we might hope to determine, illustrates the divide between clean numbers and unresolved details. The coma brightness combined with models of dust efficiency allows calculations of nuclear size. Plug in reasonable values, and you get a range between 300 meters and several kilometers. The equations are correct, the methods are established. But because the underlying assumptions about albedo and activity efficiency are uncertain, the final answer is a spread wide enough to encompass objects of dramatically different scales. We can do the math, but the math alone cannot close the gap. This tension between certainty and doubt is not unique to Atlas, but it is amplified by its status as an interstellar object. With local comets, we can test models against dozens or hundreds of other examples, comparing patterns across populations. With Atlas, the sample size is 1. Worse, it's the third sample in a set where each object has defied expectations in a different way. Oumuamua with its elongated shape and odd acceleration, Borisov with its unusual yet more conventional cometary activity, and now Atlas with its speed, chemistry, and inconsistent brightness. Instead of forming a coherent picture of interstellar wanderers, the data points scatter outward, each one introducing new uncertainties. Numbers, in astronomy, have always carried authority. From Kepler's laws to Newton's gravity, the ability to reduce motion and light to predictable quantities has been the foundation of the field. But numbers don't interpret themselves. They describe with precision, but they do not explain. Atlas embodies this paradox with unusual sharpness. Every new instrument, every new observation, every data set arrives with confidence intervals and error bars that are narrow, repeatable, and rigorous. Yet when those data sets are combined into a narrative of what this object is, the story refuses to stabilize. For example, consider the simple question of how active Atlas is. Dust production can be estimated from brightness, gas production from spectral lines, and these can be compared to solar heating at its distance. Each step involves a calculation we can trust, but the results refuse to align. The level of gas production suggests one nucleus size, while the dust output implies another. Solar heating models predict certain activity thresholds, but Atlas activates at distances where comets are normally dormant. The certainty in each number stands, but the conclusions pull apart like threads in opposite directions. The doubt in the details becomes more than an academic puzzle when we recognise that it reveals gaps in our understanding of planetary formation beyond our own system. If Atlas is truly representative of a class of objects formed under conditions different from ours, then the chemistry, size, and behaviour are telling us something profound about other planetary nurseries. But because each detail resists easy integration, the message remains garbled. It's like intercepting a signal with perfect clarity, but in a language we cannot yet translate. Astronomers are not unused to paradox. The field is filled with discoveries that first appeared contradictory before later yielding to deeper theory. The precession of Mercury's orbit made no sense until relativity explained it. The spectra of distant galaxies seemed strange until redshift revealed the expansion of the universe. Doubt in the details often precedes revolution in the framework, but with Atlas, the revolution is still out of reach. The data accumulates, the models are tested, and yet the contradictions remain unresolved. The more we learn about Atlas, the sharper this divide becomes. Certainty in the numbers reassures us that we are not mismeasuring, that the telescopes are not deceiving us, that the mathematics of orbital mechanics and spectroscopy remain sound. Doubt in the details reminds us that knowledge is not the same as understanding, that data without context can confuse as much as it enlightens. A visitor like this shows us both our strength and our limits. We can pin down its path through the sky with uncanny accuracy, while admitting that we cannot say with confidence why it looks and behaves the way it does. As Atlas continues its journey, the data stream will only grow. More spectra, more brightness measurements, more images will fill the archives. The certainty in those numbers will remain unchallenged, precise down to the decimal. But each new measurement carries the risk of deepening the doubt, of widening the gap between what we know and what we understand. That tension has become the defining feature of this interstellar object, a paradox that resists closure even as the mathematics remain solid. And with every night of observation, that paradox only sharpens, pulling us further into the realization that sometimes the more firmly we measure, the less secure our explanations become. From the very beginning, astronomers tried to fit 3i Atlas into the familiar patterns of cometary behaviour. After all, most of what we know about icy bodies comes from decades of studying comets in our own solar system. They follow predictable rules, they brighten as they approach the sun, they develop comas and tails with compositions that fall within known ratios. Their activity can be explained by sublimation of water ice and other volatiles at specific distances. The framework is solid because thousands of examples have confirmed it, so when Atlas arrived it made sense to assume it would follow the same rules, just with the added layer of being interstellar. But from the first detailed observations, that assumption began to unravel. Comets are often described as dirty snowballs, conglomerates of ice and dust that vent gas as the sun warms them. This venting creates the visible coma, the glowing atmosphere that makes comets such striking targets. For comets within our system, water ice is the main driver, with carbon monoxide and carbon dioxide contributing under certain conditions. Their ratios tell us about formation zones, about distances from natal stars, about the early chemistry of their parent systems. With Atlas, the ratios looked wrong. Instead of water dominating, it was carbon dioxide that carried the signal, at levels so extreme that water was pushed almost into irrelevance. Observing that from a distance, where water should already have been active, only deepened the confusion. It was behaving like no comet we had ever studied before. At distances of 3 astronomical units or more, most comets remain faint, barely active, because solar heating isn't strong enough to sublimate water in significant quantities. Yet Atlas displayed a bright and extended coma well before reaching those inner regions. The explanation that carbon dioxide sublimates at lower temperatures could account for some of this, but not at the observed intensity. Models of outgassing at those distances don't easily match what was measured. It seemed almost as though Atlas was overperforming, venting more vigorously than any natural body of its kind should at that stage of approach. Brightness variations added another layer. A normal comet brightens steadily as it nears the Sun, with fluctuations tied to rotation or episodic outbursts. Atlas, however, showed irregular changes that didn't align neatly with either pattern. At times it brightened more than expected, then plateaued, then dimmed, without the clear periodicity or consistent correlation with distance that models predict. Was it tumbling chaotically, presenting different active regions at odd intervals? Was there dust fragmentation altering its reflectivity? Or was there something more unusual taking place within the nucleus? The data supported multiple interpretations, none of which could be confirmed with confidence. Dust behaviour is often the key to deciphering comets. The size and velocity of ejected grains affect the coma's brightness and structure. For Atlas, dust production estimates varied significantly depending on the method used. Some suggested surprisingly low dust-to-gas ratios, which would make it chemically distinct from most solar system comets. Others indicated that the dust was unusually fine or ejected at atypical velocities. Each conclusion implied something different about the nucleus, yet none aligned perfectly with the observed coma morphology. A comet that should have revealed its secrets through dust instead deepened the mystery. Rotation should have been another straightforward property. By tracking brightness changes over time, astronomers can usually determine how long it takes a cometary nucleus to spin. That period then explains observed patterns of venting and variability. In Atlas's case, the rotation signal was ambiguous. Some datasets implied a stable spin period of several hours, while others suggested a chaotic tumbling motion, more like that seen in Oumuamua. Without a clear rotation model, predictions of its future activity became unreliable. Once again, the comet seemed unwilling to play by the rules. Even the tail presented puzzles. Its orientation and structure should follow predictable dynamics, governed by solar radiation and the solar wind. Dust tails curve, ion tails point directly away from the Sun, and their evolution is well understood, yet Atlas's tail showed inconsistencies, with features that suggested complex interactions not fully accounted for by standard models. At times, secondary streams appeared, possibly from localized outbursts, but their persistence and angles raised questions. Was this simply an extreme case of known processes, or something genuinely new? The answer remained unclear. The longer astronomers watched, the more it seemed that labelling Atlas a comet was more about convenience than accuracy. It displayed many cometary features: a coma, a tail, outgassing activity. But each of those features carried anomalies that set it apart from the thousands of comets catalogued before. Calling it a comet was like fitting a square peg into a round hole. It worked if you didn't look too closely, but the details revealed the mismatch. There were those who argued that nothing about Atlas was truly inexplicable, that with enough time the anomalies would be reconciled. Maybe its unusual chemistry reflected a birth environment different from anything in our system. Maybe its velocity was the result of cumulative gravitational scattering over billions of years. Maybe its rotation was simply hard to measure because of observational limits. These were reasonable arguments, and none could be dismissed outright. But collectively, they pointed to an object that continued to resist the neat classification we rely on to make sense of the cosmos. Comets are supposed to be messengers of the past, frozen remnants of planetary formation that tell us about conditions billions of years ago. In that sense, Atlas was a perfect opportunity. A comet not from our sun's nursery but from another star entirely, carrying chemistry from a system we may never otherwise sample. But instead of clear answers, it has given us contradictions. A chemical fingerprint unlike anything we've seen. A speed that outruns expectations. A brightness curve that refuses to stabilize. A tail that bends in ways that provoke debate. A comet that, in every measurable sense, refuses to behave as a comet should. This refusal forces astronomers to confront the limits of their models. If Atlas can't be explained by the frameworks built from studying local comets, then perhaps those frameworks are incomplete. Perhaps icy bodies across the galaxy are more varied than we imagined. Or perhaps interstellar travel imposes alterations that erase the patterns we expect. Cosmic rays, micrometeorite bombardment, thermal cycling over billions of years, each could reshape a body in ways unfamiliar to us. But whether those processes can fully account for Atlas remains unresolved. In some ways, this makes Atlas even more valuable. A normal comet from another system might have expanded our knowledge incrementally. This one, by refusing to behave, forces us to rethink fundamentals. It challenges assumptions about cometary activity, about chemistry, about the outcomes of planetary formation across the galaxy. It reminds us that our categories are human constructs, useful but not universal, and that nature often refuses to conform to the boxes we build. The refusal also feeds speculation. If it doesn't act like a comet, is it truly a comet at all? The notion that it might be artificial has been raised, though not widely accepted. Still, the very fact that the discussion exists reflects how far Atlas has strayed from expected behaviour. An ordinary comet wouldn't provoke such thoughts. Only an object that resists explanation so thoroughly could inspire serious debate about whether it is what it appears to be. As Atlas continues on its path, it carries these contradictions with it. Observatories around the world log its behaviour night after night, each team hoping that the next data set will bring clarity. Yet clarity has been elusive. Instead, the catalogue of anomalies grows. More details that refuse to align. More measurements that complicate rather than confirm. The comet that refuses to behave has become a symbol of the gap between certainty in data and uncertainty in meaning. And in that gap lies the realization that sometimes the universe delivers its most profound lessons, not through answers, but through stubborn refusal to fit the patterns we expect. From the very first orbital solutions, the trajectory of 3i Atlas looked straightforward, hyperbolic, inbound from the dark between the stars, swinging through the solar system, outbound again to rejoin the galactic void. The calculations were precise, the path undeniable. In terms of mechanics, this was one of the cleanest aspects of the entire discovery. The gravitational math held, the numbers converged, and the results left no ambiguity. But as always with Atlas, the deeper the certainty in one aspect, the greater the confusion in another. A trajectory can be mapped with exquisite detail, but the history that produced it cannot. And in this case, the attempt to explain how Atlas arrived on the orbit we observe has revealed puzzles as deep as any of its chemical or photometric mysteries. Its velocity tells the first part of the story. 61 kilometers per second in excess of solar escape velocity. meaning that even after accounting for the sun's gravity, it carries a residual pace that dwarfs most natural wanderers. For comparison, Oumuamua's excess velocity was around 26 kilometers per second. Borisov carried 32, Atlas nearly doubles both. We can calculate that with ease, but explaining it is another matter. A body moving that fast requires a past filled with extraordinary events. Perhaps ejection from a young system where giant planets reshaped orbits chaotically, perhaps scattering by multiple stellar encounters over billions of years, perhaps something we have not yet identified. The problem is not in measuring the numbers, but in tracing the story behind them. If Atlas was ejected from its natal system by planetary dynamics, then the speed should fall within predictable ranges based on simulations of early planetary systems. But most models top out below what Atlas carries. Even violent interactions with gas giants tend to produce escape velocities somewhat lower. Some scenarios involving close stellar flybys can push speeds higher, but those cases are rare and would require just the right conditions. Did Atlas originate in such a chaotic environment, or are we seeing something that forces us to adjust our models of system formation? The numbers don't say. They only confirm the result, not the cause. The angle of approach deepens the puzzle. Objects bound to the sun tend to cluster around the ecliptic, the plane of planetary orbits. Interstellar visitors, by contrast, can come from any direction, but statistical arguments suggest certain orientations should be more common. Atlas, however, arrives on a trajectory tilted in ways that suggest origins in the thick disk population of our galaxy, an older stellar cohort with less orderly motions. If that's correct, then this object may have been travelling for billions of years, older than our solar system itself, wandering across regions where gravitational encounters accumulated. That could help explain its velocity. Yet again, the details resist confirmation. Its path is clear, its history is opaque. Another complication arises when we compare the trajectory to expectations based on galactic motion. Stars orbit the galactic centre in patterns shaped by age and population. Local thin disk stars like the Sun move in relatively orderly directions, while thick disk members scatter with more random velocities. Atlas fits more comfortably with the latter, which suggests an origin long ago in a population formed when the Milky Way was still turbulent. That explanation makes sense, but it forces us into uncomfortable timescales. If Atlas is truly that old, it may have crossed the galaxy multiple times, surviving encounters that should have destroyed smaller bodies. Why this one endured when so many others must have perished remains unclear. Even within the solar system, its trajectory holds subtleties. Non-gravitational accelerations from outgassing are common in comets. As jets of gas escape, they push the nucleus slightly, creating deviations from purely gravitational motion. For Atlas, measuring such deviations has been a priority. Yet the signals remain ambiguous. Some analyses suggest tiny shifts inconsistent with expected levels of outgassing. Others see no significant deviation at all. The data is not precise enough to settle the matter, leaving room for speculation. If the motion matches pure gravity too closely, does that suggest unusually symmetric venting or a level of inactivity inconsistent with its bright coma? If deviations exist but don't match solar heating patterns, what does that imply? Again, the trajectory can be measured. The explanation refuses to stabilize. One striking realization is that while we can chart where Atlas will be in the coming months and years with near-perfect accuracy, we cannot say with certainty where it came from. Backward integrations of its orbit through galactic models scatter the probabilities across vast swaths of space. There is no clear natal star we can point to. The uncertainties multiply as we extend the calculations farther into the past until the trail dissolves entirely. This is not unusual for interstellar objects, but it reinforces the strange duality of certainty and doubt. The forward path is crystal clear. The backward path is lost in fog. For astronomers, this creates a peculiar tension. On one hand, Atlas represents a triumph of precision. We can tell you where it will be on October 29th down to the arcsecond. On the other, it represents the limits of reconstruction. We cannot tell you which stellar nursery birthed it, or which encounters sculpted its current course. That lack of context makes its behaviour harder to interpret. Is the extreme velocity typical for its class, or an outlier? Is its chemistry the signature of its birthplace, or of billions of years of alteration along a wandering path? Without knowing the trajectory's history, the details cannot be fully understood. The comparisons to Oumuamua and Borisov make the contrast even sharper. Oumuamua's trajectory included small deviations that sparked debates about outgassing or artificial propulsion. Borisov followed a cleaner cometary path, showing natural accelerations explainable by venting. Atlas, despite its vigorous activity, seems almost too clean in its motion, or at least too ambiguous for certainty. This mix of extremes, high speed, unusual chemistry, uncertain non-gravitational effects, places it in a category of its own. For those inclined toward speculation, trajectories that resist explanation become fertile ground. If Oumuamua raised the question of whether some interstellar objects might be artificial, then Atlas feeds the same imagination. An orbit that looks natural yet carries anomalies opens the door to thought experiments. Could an advanced civilization engineer a trajectory to mimic natural hyperbolic motion? Could the apparent perfection of its path be intentional rather than incidental? These questions remain in the speculative realm, and most astronomers emphasize natural explanations. But the persistence of unexplained details keeps the discussion alive. The refusal of Atlas's trajectory to yield a clear history also reminds us how little we know about the true population of interstellar objects. 3 confirmed detections do not define a distribution. We don't yet know how common such wanderers are, what range of velocities they carry, or how diverse their orbits can be. Future surveys may fill in those gaps, showing whether Atlas is unusual or representative. But for now, it stands as an isolated data point that disrupts expectations rather than confirming them. As it continues on its course, observers will refine measurements, seeking any signs of deviation, any anomalies in acceleration, any hints that might illuminate the processes at work. But given the short observational window and the limits of our instruments, many of those questions will remain unresolved. The trajectory will remain a paradox, a path mapped with precision, yet resistant to explanation. We know exactly where it is going. We do not know why it moves the way it does. That gap between certainty and understanding is what defines Atlas more than any single number. And so, the story continues, with telescopes chasing its path across the sky, logging data that confirms the orbit while deepening the mysteries of its origin. A trajectory without explanation is more than a scientific curiosity. It is a reminder that motion itself can carry secrets, that the paths objects trace across space encode histories we cannot always decode. Atlas follows its line through the solar system with mathematical clarity, and yet behind that line stretches a past we cannot reconstruct, a set of encounters and forces that remain hidden. The numbers give us certainty. The meaning remains elusive, and in that unresolved tension lies the strange allure of a visitor that refuses to be fully understood. From the earlier spectroscopic measurements, the chemistry of 3i Atlas began to diverge from expectations. Every comet has its own fingerprint, but most fall into patterns that decades of study have made familiar. Water dominates the emission lines, with carbon monoxide and carbon dioxide as supporting actors, joined by smaller quantities of hydrocarbons, ammonia, and other volatiles. The ratios vary, but the script remains recognizable. With Atlas, that script was thrown off balance almost immediately. Observations from the James Webb Space Telescope revealed a composition in which carbon dioxide overwhelmed water to an extent not previously seen. A CO2 to water ratio of nearly 80 to 1 defied conventional models of cometary formation. It's not that carbon dioxide is rare in comets. Many exhibit significant CO2 activity, especially at greater distances where water remains frozen. But the sheer dominance of CO2 in Atlas was something else entirely. Water, normally the central driver of a comet's coma, seemed nearly absent in comparison. For an interstellar object, this raised immediate questions. Did Atlas form in a region where CO2 condensation dominated, perhaps farther from its parent star than most comets in our system? Did it originate in a disk with different chemistry, where water was less abundant or locked in ways that suppressed its sublimation? Or had billions of years of interstellar exposure altered its surface to favour CO2 release over water? Each explanation was possible, yet none was fully convincing. The distance at which activity was first detected added to the puzzle. Atlas began showing significant CO2-driven outgassing beyond 3 astronomical units, when water sublimation should still be minimal. That alone wasn't unprecedented, but the intensity was unusual. A body venting so strongly at such a distance implied either a composition rich in supervolatiles or internal structures that facilitated their escape. But if that were the case, why was water so suppressed? Normally, as the comet moves inward, water activity overtakes CO2. With Atlas, the ratios remained skewed in a way that refused to match expectations. Another layer came from comparisons to known outliers. Comet C 2016 R2, for example, displayed elevated carbon monoxide and nitrogen species, marking it as unusual but still within a conceivable framework. Atlas, however, pushed those boundaries farther. Its chemistry didn't simply stretch the model, it seemed to contradict it. One explanation proposed that cosmic ray bombardment during its long interstellar journey had altered its surface, creating a crust that trapped water while allowing CO2 to escape. Another suggested that dust mantling from repeated heating cycles insulated deeper ices, biasing the observed emissions. But even those scenarios couldn't fully reconcile the ratios. The lack of consistency across observational methods deepened the uncertainty. Infrared spectra painted one picture, while photometric modelling implied another. Ground-based observations reported signals that sometimes conflicted with space-based results. None of this suggested error or incompetence. The measurements themselves were sound. But the interpretation became a shifting puzzle. Every attempt to fit the numbers into a coherent chemical narrative produced new contradictions. For cometary scientists, this was more than an inconvenience. Chemistry is the key to unlocking origins. Ratios of water to CO2 to CO, along with trace species, provide clues about where in a protoplanetary disk an object formed. They tell us about temperatures, radiation environments, and the distribution of volatiles. When an object arrives from another star system, its chemistry becomes even more valuable, a direct sample of alien planetary formation conditions. Atlas should have been a treasure trove of such information. Instead, it presented a chemistry so unusual that the clues pointed in conflicting directions. It told multiple stories at once, and no clear way to decide which was correct. Some argued that perhaps our models of volatile distributions in protoplanetary disks are simply too narrow. After all, most are based on observations of our own system, supplemented by a handful of exoplanetary studies. If disks around other stars produce wider chemical diversity, then Atlas might simply reflect that variety. Others countered that the ratios were too extreme even for that explanation, and that some process during its long interstellar voyage must have reshaped its composition. The debate remained unresolved, highlighting once again the gap between certainty in data and doubt in meaning. Water, in particular, became the focal point. On Earth and in our system, water is the default volatile. It shapes comets, drives activity, and dominates spectra. But Atlas treated water as a secondary player, almost irrelevant. Was this simply a matter of surface depletion, with deeper reserves yet to reveal themselves as it moved closer to the Sun? Or was it intrinsic? a sign that the environment where it formed produced far less water ice relative to CO2. The difference mattered because the first pointed to evolutionary processing, while the second pointed to fundamental differences in planetary system chemistry. Adding to the confusion, the ratio didn't seem to evolve the way it should as the comet neared perihelion. Normally water activity ramps up and eventually dominates. Atlas continued to show CO2 dominance, resisting the transition. That persistence suggested something more profound than surface effects. If true, it would mark Atlas as not merely an outlier, but a fundamentally different kind of object. Dust chemistry provided few answers. Analysis of coma grains showed expected silicates, but with abundances that didn't clarify the volatile story. Without in situ sampling, we remain limited to indirect inference, and with every attempt the contradiction sharpened. Models of crust evolution, mantle development and radiation processing could each account for part of the picture, but none explained the whole. This left some researchers to wonder whether the categories we use to describe comets are too rigid. If Atlas is a product of conditions we've never encountered, perhaps trying to fit it into existing frameworks is the problem. Instead of forcing it into known models, maybe we need to expand those models to allow for objects with compositions this extreme. That would mean acknowledging that the chemistry of interstellar comets might occupy a spectrum far broader than anything we've imagined. Others lean toward evolutionary explanations. Billions of years drifting between stars would expose Atlas to cosmic rays, micrometeorite bombardment, and temperature cycles unlike anything our local comets experience. Such exposure could alter chemistry in ways that are poorly understood. But even here, the ratios push the limits of plausibility. How could water, so abundant and resilient, be suppressed so thoroughly without CO2 being destroyed as well? The mechanisms didn't add up. The possibility of artificiality once again hovered at the edge of discussion, not because the chemistry screamed technology, but because its refusal to conform tempted speculation. Could the ratios represent deliberate engineering, designed to mimic cometary behaviour while concealing something more? Most astronomers dismissed this, noting that exotic natural processes are more likely than advanced engineering. But the very fact that the question arose reflected the extent of the anomaly. For the scientific community, the chemistry of Atlas has become a case study in how data can challenge models. We can measure with exquisite precision. We can catalogue every line, every ratio, every trace. But when those numbers refuse to align with theory, we're forced to admit the limits of our understanding. Atlas is a reminder that our frameworks are provisional, that nature often resists categorization, and that sometimes the chemistry tells us more about what we don't know than about what we do. As Atlas moves farther from the sun and fades from view, the data sets will be archived, analysed, and reanalyzed. The CO2 dominance will remain a striking anomaly, a marker of difference that cannot be ignored. Whether it eventually forces a revision of models or simply stands as an unexplained outlier remains to be seen. What is certain is that the chemistry of Atlas has already reshaped how astronomers think about interstellar visitors. Instead of offering clarity, it has forced confrontation with the unknown, and in that confrontation lies the realization that even the simplest molecules, when arranged in unexpected ratios, can defy our models and leave us with more questions than answers. Brightness is often the most basic property an astronomer can measure. Before spectra, before composition, before detailed dynamics, there is the simple record of how much light an object reflects or emits. For comets, this brightness evolves in ways that are both familiar and interpretable. As they approach the sun, they brighten, sometimes steadily, sometimes in bursts, but always within a framework that makes sense. The light curve becomes a window into size, activity, rotation, and sometimes even internal structure. With Atlas, the light curve has been anything but straightforward. The numbers are clean, the measurements precise, but the story they tell is filled with contradictions. At first, the pattern looked promising. When it was still distant, Atlas brightened faster than expected, hinting at early activity. This was consistent with its carbon dioxide dominance, since CO2 sublimates at lower temperatures than water. The initial narrative was simple: an interstellar comet that begins venting earlier than most solar system examples, driven by unusual chemistry. But as observations accumulated, the curve began to fracture. Instead of a smooth increase, the brightness fluctuated irregularly. At times it plateaued when models predicted growth. At other times it spiked abruptly without clear cause. The light curve stopped behaving like a typical cometary response to solar heating and started to resemble something far less predictable. Astronomers attempted to fit rotational models to the fluctuations. If the nucleus was spinning, different active regions could rotate into sunlight, causing variations in brightness. This approach has worked for countless comets and asteroids, but with Atlas, the signals were inconsistent. Some datasets suggested a rotation period of several hours. Others pointed to chaotic tumbling, more like a body that had been knocked off balance and now spun unpredictably. Neither interpretation explained the whole set of observations. The brightness shifts were too irregular for a single stable period, yet too patterned to be entirely random. Coma morphology complicated things further. High-resolution imaging showed diffuse structures in the coma that hinted at jets or localized sources of gas and dust. These features should have produced corresponding brightness changes, and in some cases they did. But in other cases the coma appeared relatively stable while the light curve shifted sharply. The mismatch suggested that not all of the variability could be traced to visible structures. Something deeper within the nucleus might be driving changes that only appeared in integrated brightness, not in visible morphology. Dust played its role as well. The scattering of sunlight by grains contributes heavily to observed magnitude. Variations in dust size distribution, production rate, or fragmentation could explain irregularities. Some models proposed that Atlas was releasing unusually fine dust that reflected more efficiently, creating sudden spikes. Others suggested that clumps of material fragmented unpredictably, releasing bursts of reflective grains. But once again, no single explanation covered all the behaviour. At times, the dust seemed too weak to explain the brightness levels, at other times too strong to match the gas output. The irregular light curve forced astronomers to consider whether they were seeing the product of multiple processes acting simultaneously. Perhaps rotation was contributing, but complicated by chaotic tumbling. Perhaps dust bursts layered atop CO2 venting, with thermal stresses triggering unpredictable fragmentation. Perhaps cosmic ray processing of the surface had created crusts that fractured unevenly. Each explanation added plausibility, but also complexity, and the more complexity added, the less elegant the narrative became. Comparisons to other interstellar visitors highlighted the differences. Oumuamua, though lacking a coma, also displayed puzzling light curve variations that suggested an elongated shape and possible tumbling. Borisov, by contrast, behaved much like a conventional comet, with brightness rising predictably as it neared the sun. Atlas fell somewhere in between, with activity but no stable pattern, producing irregular fluctuations that resisted classification. Instead of clarifying the picture of interstellar bodies, it muddied it further. What made the situation more difficult was that brightness is one of the most universally measured properties. Dozens of observatories tracked Atlas nightly, producing overlapping light curves. The volume of data was enormous, the precision high, and yet all that information failed to converge on a simple interpretation. It was a case where more data didn't equal more clarity. Instead, the accumulation of numbers sharpened the contradictions. The same object could look steady in one dataset and wildly variable in another, depending on timing, filters, and calibration. Some astronomers suggested that Atlas might be in a state of partial disintegration. Comets occasionally fragment, breaking into smaller pieces that increase surface area and temporarily boost brightness. If Atlas was slowly shedding fragments, that could explain some of the irregular changes, but fragmentation usually leaves visible signatures, secondary nuclei, altered coma shapes that weren't consistently observed. If it was breaking apart, it was doing so in a way unlike typical solar system examples. Another avenue of interpretation focused on phase effects. The way sunlight reflects from irregular surfaces can produce variations that complicate brightness predictions. If Atlas's nucleus had unusual geometry, with facets or cavities reflecting light at odd angles, it could generate irregular curves. This was considered plausible, but it didn't explain the apparent bursts that exceeded what phase effects alone could account for. The deeper question beneath all these attempts was whether Atlas's light curve represented something fundamentally new or just an extreme case of known processes. If it was new, then it hinted at diversity in interstellar bodies far greater than we expected. If it was extreme, then it tested the limits of existing models, forcing refinements. Either way, the curve defied the simplicity that astronomers usually count on for brightness evolution. What made this particularly frustrating was the sense that brightness should be the easy part. Compared to chemistry or trajectory history, measuring how much light an object reflects seems straightforward. Yet here was an interstellar comet turning the simplest property into one of the most perplexing. The light curve became a symbol of the broader paradox: certainty in measurement, uncertainty in meaning. Even as Atlas moved closer to perihelion, the curve failed to settle. Spikes, plateaus, and unexpected dips continued to appear. Some predicted that water activity would eventually take over and smooth the variability. But water never asserted itself in the way it should have, leaving CO2 dominance intact and irregularity unresolved. Each stage that should have clarified the pattern instead reinforced the strangeness. The longer the monitoring continued, the more Atlas demonstrated that brightness was not a passive property, but an active expression of its complex and poorly understood interior. Light curves that should have been guides became riddles. Peaks that should have marked simple rotation became confounding signals. Declines that should have indicated fading activity instead contradicted chemical evidence. The dark, rather than revealing the truth through light, only deepened the mystery. And yet, astronomers persisted, because brightness is all we can measure when nothing else is possible. Long after spectroscopic instruments shift away, smaller telescopes will still record the flickering light of Atlas as it recedes into the dark. The light curve will remain an enduring data set, waiting for theories that may one day explain what we saw. But for now, the story of Atlas's brightness is one of contradictions, a curve drawn in the dark that defies the models meant to interpret it. Velocity has always been one of the most revealing properties of celestial objects. From orbital speeds we learn about gravitational binding. From excess velocities we infer histories of ejection, and from peculiar motions we trace past encounters. For interstellar visitors, speed is the defining trait. It is what distinguishes them from ordinary comets and asteroids, what sets them apart from the endless parade of solar system wanderers. Oumuamua entered with a respectable 26 km per second beyond solar escape. Borisov carried 32. Both values fit comfortably within the expectations for objects scattered from planetary systems and drifting across galactic space. Atlas, however, arrived carrying 61 km per second in excess of what the Sun's gravity could restrain. Twice the speed of its predecessors, nearly uncomfortably high for natural scenarios. A speed that, while not impossible, stretches the plausibility of conventional models. From a purely mechanical perspective, the trajectory is perfectly valid. Hyperbolic orbits with excess velocities of 60 or more kilometers per second are not forbidden by physics. The equations work, the path is stable, the numbers check out. But when we attempt to reconstruct the events that could have launched an object onto such a course, the explanations begin to thin. Ejection from a planetary system is the most obvious mechanism. Young stars surrounded by gas giants can sling comets outward during chaotic migrations, scattering them into interstellar space. Simulations of such processes produce distributions of ejection speeds, but most cluster below what Atlas carries. Only rare and extreme cases reach its level, and those often require planetary configurations that verge on unstable. Did Atlas truly originate in such a volatile nursery, or is there something we're missing about how common these conditions might be? Another mechanism is stellar encounters. When stars pass near one another, their gravitational fields can exchange small bodies, flinging comets outward at new velocities. Such interactions happen often in the dense environments of stellar birth clusters, where stars form in proximity. But even here, the speeds produced are usually lower than Atlas exhibits. To reach 61 kilometers per second, the encounter would need to be unusually close, with just the right geometry. Possible, yes, but improbable. If Atlas is the third interstellar visitor we've detected, how likely is it that one of them already falls into such an improbable case? Unless, of course, we have selection bias, detecting only the fastest because they are easiest to notice before fading into the dark. That explanation has merit, but it still doesn't erase the sense of unease that comes with Atlas's extraordinary pace. Galactic dynamics adds another layer. Stars orbit the galactic centre at different velocities depending on their populations. Thin disk stars like our Sun move in relatively orderly paths, while thick disk and halo stars scatter with more eccentric motions. Objects ejected from systems belonging to those older populations may carry higher velocities relative to the Sun. Atlas's trajectory aligns loosely with that scenario, hinting at an origin in a population long predating the Sun. That would make its high speed less surprising. But it also raises questions about survival. If Atlas has been travelling for billions of years across the galaxy, enduring repeated encounters with radiation, dust and stars, how has it remained intact? Smaller bodies should erode, fragment or disintegrate over such spans. Atlas is here, measurable and active, a survivor that seems too pristine for its supposed age. The chemistry complicates the velocity further. If it were truly ancient, drifting for eons, we might expect a heavily altered surface, a suppression of volatile activity, and a coma muted compared to younger comets. Instead, Atlas displays vigorous CO2 venting bright and extended activity, inconsistent with the idea of an exhausted traveller. Could its speed indicate a more recent ejection, making it younger than its trajectory suggests? If so, then what explains the magnitude of its excess velocity? We circle back to the same problem. The speed shouldn't be this high for an object behaving this way. When astronomers run simulations of planetary systems ejecting comets, they can produce distributions of velocities. Most fall below 30 kilometers per second. A tail of the distribution stretches higher, but rarely do they exceed 50 without implausible configurations. Atlas's 61 sits in that uncomfortable space where it is not impossible, but not easily justified. Each new attempt to reconcile it ends up feeling like a stretch. The simplest models fail, the more complex ones demand assumptions stacked upon assumptions. The result is an object that feels out of place, a wanderer moving faster than it should. Comparisons to Oumuamua and Borisov make the contrast sharper. Both were mysterious in their own ways, but their velocities did not strain credibility. They were anomalous in shape, chemistry or activity, but their motions were ordinary. Atlas flips the script. Its activity and coma confirm its cometary nature, but its speed puts it at the edge of explanation. This inversion makes it harder to categorize. We could dismiss Oumuamua's strangeness as the product of observational limits, Borisov's as an exotic but comprehensible case. Atlas resists that comfort. Its velocity insists on attention, forcing astronomers to confront the possibility that our expectations for interstellar objects may be far too narrow. One way to ease the discomfort is to invoke the vastness of galactic time. Billions of years of wandering provide opportunities for cumulative effects. Multiple scattering events, interactions with stars, encounters with molecular clouds, all could gradually elevate an object's speed. But cumulative scenarios raise their own doubts. Random encounters can increase velocity, but they can just as easily decrease it. Over long timescales, the distribution should average out, not climb toward extremes. To explain Atlas, we need a sequence of rare events stacking in the same direction, unlikely but not impossible. Perhaps Atlas is simply a statistical outlier, one that happened to land in our view. But then we're left with the question of why our first few detections include so many anomalies. Outliers should be rare, yet all three interstellar visitors have strained categories in one way or another. Speculation once again finds fertile ground here. A speed that seems too high for natural explanations invites questions about whether natural is the only option. Some argue that the clean hyperbolic trajectory of Oumuamua raised similar thoughts, though most evidence still favours natural origins. With Atlas, the debate resurfaces. Could an object be engineered to travel at such a speed, mimicking cometary appearance while carrying other purposes? Few astronomers endorse this seriously, preferring to exhaust natural explanations. Yet the speed keeps the door open, if only because the gap between models and reality remains so wide. More practically, Atlas's velocity limits our ability to study it. The faster it moves, the shorter the window of opportunity. Every observation campaign is compressed, every chance to gather data narrowed. The high speed becomes not only a scientific puzzle, but a practical frustration, rushing the object past our instruments before we can fully probe its mysteries. We are left scrambling to record what we can, knowing that the trajectory will soon carry it beyond reach. The irony is sharp. The very property that makes Atlas so puzzling also ensures that it will escape our scrutiny before we can resolve the contradictions. In the end, the speed of Atlas encapsulates the broader theme of this entire encounter. The numbers themselves are solid, precise, undeniable. 61 kilometers per second is not an estimate with wide uncertainty. It is a measurement grounded in repeated calculations. But the meaning of that number, the history it encodes, remains obscure. We can state with certainty how fast it moves, yet we cannot explain with confidence why it moves so fast. The speed should not exist within the comfortable margins of our models, and yet it does, flashing across the solar system as proof that reality often exceeds expectation. As Atlas races outward, that speed will carry it into the dark, away from the sun and away from us, perhaps never to be seen again. The data will remain, archived and debated, but the object itself will be gone, its rapid passage leaving only questions behind. Speed, which should have been the simplest of properties to interpret, becomes instead one of the deepest enigmas. A number carved into its trajectory, undeniable yet unexplained, a reminder that the universe often moves faster than our understanding can follow. One of the most basic questions astronomers ask about a new object is how big it is. Size sets the scale for everything else: mass, surface area, potential activity, survivability over time. For a comet, the nucleus diameter can usually be constrained by combining brightness measurements with assumptions about reflectivity and gas production. Thousands of comets have been characterized this way, with ranges that usually narrow as more observations accumulate. With Atlas, however, size has proven elusive. Every attempt to pin down its nucleus yields results so wide and contradictory that the very notion of scale seems to dissolve. A body that could be a few hundred meters across or several kilometers large creates different narratives of its past, and Atlas refuses to choose between them. The challenge begins with brightness. The most direct method to estimate size is to measure how much sunlight the object reflects. A brighter nucleus implies a larger surface, or a smaller one with high albedo. But comets complicate this because the coma contributes the majority of observed light. Distinguishing the nucleus's intrinsic brightness from the surrounding cloud of dust and gas is never straightforward, and in Atlas the coma is unusually active and extended. Attempts to isolate the nucleus signal from coma contamination lead to wildly different estimates depending on the model applied. Some suggest a nucleus smaller than 500 meters, others propose diameters closer to 4 or 5 kilometers. The difference between those scales is enormous. The difference between a fragment barely surviving and a mountain-sized block of ice. Dust production is supposed to help refine these guesses. The amount of dust a comet releases is linked to surface area, gas output, and solar heating. If we know how much material is being ejected, we can back-calculate the size needed to sustain that activity. For Atlas, though, the numbers conflict. Gas production rates imply one value, dust output another. Some analyses show a nucleus too small to support the observed coma, unless it is venting at implausibly high efficiency. Others suggest a larger body shedding dust at lower rates. Each possibility fits part of the data but contradicts another. Instead of convergence, the models diverge. Rotation usually offers another angle. Brightness variations caused by spinning nuclei can reveal surface irregularities and dimensions. An elongated object produces stronger fluctuations than a spherical one, and the amplitude of the curve can constrain size. With Atlas, the fluctuations exist but remain inconsistent, producing no reliable rotation period and no clear amplitude relationship. The result is that size estimates based on rotation are as uncertain as those based on brightness. The data confirms variability, but the variability itself defies interpretation. Infrared observations might have provided clarity, since thermal emission depends on size as well as surface properties. But even there, Atlas refused cooperation. Infrared fluxes were too entangled with dust contributions and reflective uncertainties to yield definitive results. Models produced size ranges overlapping but not narrowing the earlier optical estimates. Instead of reducing the spread, they simply confirmed how uncertain it was. This ambiguity has significant implications. A nucleus only a few hundred meters across would struggle to survive billions of years of interstellar travel. It would be vulnerable to cosmic rays, collisions with dust, and thermal cycling. If Atlas is that small, its survival implies either a younger age or unusual resilience. A larger nucleus, on the order of kilometers, would be far more plausible as a long-term survivor, but then its CO2 dominance and vigorous activity become harder to explain without water contribution. Each size range solves one problem, but creates another, leaving astronomers without a stable interpretation. The comparisons to previous visitors underscore the contrast. Oumuamua was estimated at about 100 meters, though its elongated shape made precise determination difficult. Borisov's nucleus was several kilometers across, aligning with solar system comets. Both cases, while uncertain, fell within ranges that made sense. Atlas spans both categories, creating a blurred picture where it could be either a scaled-up version of Oumuamua or a scaled-down version of Borisov. The inability to place it firmly into either group disrupts attempts to build a coherent taxonomy of interstellar comets. Some researchers propose that the uncertainty reflects not just observational limitations, but intrinsic properties of the object. If Atlas has a highly irregular shape, with large variations in reflectivity across its surface, then brightness-based estimates could easily mislead. If its coma is produced asymmetrically, dust models could exaggerate or understate nucleus size. If its crust is patchy, thermal emissions could fail to represent the whole. In this view, Atlas is not a neat sphere waiting to be measured, but a chaotic body whose complexity defeats simple scaling laws. That explanation preserves naturalism, but at the cost of admitting that we may never know its true size with confidence. The consequences extend beyond academic curiosity. Size determines mass, and mass influences how much the nucleus is altered by activity, how resistant it is to fragmentation, and how representative it is of its parent population. If Atlas is small, it might be a fragile shard, a fragment from a larger body disrupted long ago, now masquerading as a comet. If it is large, It could be a robust survivor carrying intact chemistry from its natal system. Without knowing which, interpretations of its significance remain divided. The problem also feeds back into its trajectory. A small, low-mass body would be more susceptible to non-gravitational accelerations from outgassing. A larger one would follow a purer gravitational path. Measurements of Atlas's orbit show little deviation from gravity, but if the nucleus is small, that becomes harder to explain. Once again, size uncertainty collides with other anomalies, amplifying contradictions instead of resolving them. Astronomers have attempted to narrow the range by combining all data sets into composite models, but the result is not convergence on a single answer, but multiple viable scenarios. Each scenario explains some fraction of the evidence but fails on others. The larger the nucleus, the harder it is to reconcile with CO2 dominance. The smaller the nucleus, the harder it is to reconcile with stability and survival. In both directions, the contradictions grow. For those inclined towards speculation, the inability to pin down size opens doors to stranger ideas. An artificial body could be designed to mimic brightness, curves while concealing true scale. A hollow object might produce misleading signals. Such suggestions remain outside mainstream acceptance, but the persistence of ambiguity fuels them. Natural explanations strain but remain possible, yet the frustration lies in the refusal of Atlas to let itself be measured by one of the simplest properties. The longer the campaign of observation continued, the clearer it became that size, which should have been one of the easiest answers, was in fact one of the hardest. Every instrument, every method, every attempt added numbers to the record, but none settled the debate. Instead of clarity, astronomers were left with a sliding scale, a blurred image that refused to come into focus. The object that should have been either small and fragile or large and stable managed to appear as both, depending on which dataset you trusted. This uncertainty carries lessons. It reminds us that measurement is not the same as knowledge, that even something as seemingly basic as size can dissolve under the complexity of real phenomena. It forces us to confront the limits of our models and instruments, to recognize that sometimes the cosmos will not yield answers no matter how hard we press. Atlas, in its refusal to let us pin down its size, becomes not just a cometary puzzle, but a reflection of the broader struggle between certainty in numbers and doubt in interpretation. As Atlas recedes, its brightness will fade, making size estimates even harder. The final numbers entered into catalogues may settle on a range, but not a definitive value. Astronomers will continue to argue over whether it was closer to a fragment or a mountain, whether it represented fragility or resilience. But the truth, hidden within that unresolved ambiguity, will remain out of reach. A size we cannot pin down, a scale that dissolves as we measure it, a reminder that even the simplest questions can carry no simple answers. Every comet we observe within the solar system carries the weight of time. They are relics of formation, icy fragments that have survived for billions of years in deep freeze, orbiting silently in the outer regions until some perturbation nudges them inward. Their ages are measured not in centuries or millennia, but in spans that rival the solar system itself. With Atlas, however, the concept of age stretches further still. This is not a body born of our sun's nursery, but of another star entirely, carrying a history that may predate Earth, the planets, and even the sun itself. When astronomers attempt to place Atlas on a timeline, the numbers become almost incomprehensible. The object could have been travelling for billions of years before arriving here, perhaps longer than humanity has existed as a species, perhaps longer than the solar system has existed at all. The trajectory hints at this vastness. Its high velocity relative to the Sun suggests origins in the thick disk population of the Milky Way, a group of stars formed earlier than the thin disk that includes our own system. If that is correct, Atlas could be older than the solar system by billions of years, a fragment born in an environment of intense stellar formation when the galaxy itself was younger and more turbulent. That possibility places it not merely outside our system in space, but outside our system in time. A body from an era when the Milky Way structure was still assembling, now drifting into our telescopes after an incomprehensible voyage. Survival over such timescales is itself remarkable. Small icy bodies are fragile things, vulnerable to cosmic rays, micrometeoroid collisions, and thermal cycling as they pass through varying interstellar environments. Over billions of years, most would erode, fragment, or disintegrate entirely. That atlas remains intact enough to display vigorous activity challenges assumptions about longevity. If it is truly ancient, what mechanisms preserved it? Was it larger once, eroded down to its present uncertain size? Did protective crusts form to shield volatile interiors, allowing them to survive? Or is Atlas younger than its trajectory suggests, expelled more recently from its natal system? Each possibility reflects a different narrative, and each raises new questions. Cosmic ray processing provides one line of speculation. Over billions of years, high-energy radiation bombards the surfaces of interstellar bodies, altering chemistry, creating crusts, and depleting volatiles. If Atlas had been wandering for that long, we might expect a muted, exhausted nucleus, its gases locked away or destroyed. Instead, we see strong CO2 venting, a coma bright and extended. This implies that the interior has remained insulated, protected beneath layers of processed material, and that recent heating by the sun is releasing reserves preserved since formation. But if so, the persistence of such reservoirs after unimaginable spans of time remains astonishing. Dust mantling may help explain it. Comets often develop insulating crusts as volatile ices sublimate, leaving behind non-volatile material that shields deeper layers. If Atlas carried such a mantle during its interstellar voyage, it could have protected water and CO2 for billions of years. But this also raises problems. Why then is water so suppressed compared to CO2? Why does the chemistry not match what we would expect from long-term insulation? Instead of smoothing anomalies, age seems to amplify them. There is also the question of how many encounters Atlas may have experienced. In billions of years of galactic wandering, it would likely have crossed through multiple stellar neighbourhoods, passed near other stars, drifted through molecular clouds, and been subjected to countless gravitational nudges. Each encounter carries the possibility of destruction, fragmentation, or ejection into new trajectories. For Atlas to survive intact through such a gauntlet seems improbable, yet improbable survival is the only explanation consistent with its arrival here. We are left marvelling at a resilience that strains credibility, as though this fragment has endured odds stacked heavily against it. Some astronomers argue that perhaps Atlas is not as old as its trajectory implies. It could have been ejected more recently in cosmic terms from a system not far away. A recent ejection would explain its preserved chemistry and activity, making survival easier to accept. But then we are forced to ask why its velocity is so extreme. Recent ejections from typical systems should produce lower speeds. Reconciling youth with velocity becomes as difficult as reconciling age with survival. The paradox persists, whichever direction we push the interpretation. The age question also carries implications for what Atlas represents about the galaxy. If it is ancient, then it's a messenger from a time long before our own, carrying chemical records of environments we cannot otherwise sample. Its CO2 dominance may reflect conditions in primordial disks very different from our solar systems. If it is younger, then it is evidence that planetary systems continue to produce and expel comets with properties unlike ours. In both cases, the lesson is profound, but the inability to decide which scenario applies keeps the lesson obscured. Comparisons to Oumuamua and Borisov are once again instructive. Oumuamua's muted activity and unusual shape suggested significant processing, consistent with an older age. Borisov's vigorous water-driven activity suggested a younger ejection, a fresher body. Atlas straddles these categories, showing vigorous CO2 activity like a young comet, but carrying a velocity and trajectory suggestive of ancient wandering. It is both at once and neither fully, and the age beyond comprehension becomes a blur, refusing to resolve into a clear narrative. For scientists, this creates an uncomfortable gap. Models of planetary formation and interstellar object populations depend on timescales. Knowing whether most interstellar comets are ancient survivors or recent ejecta shapes our understanding of how systems evolve. Atlas provides data, but that data points in conflicting directions. Each measurement deepens the ambiguity, leaving age not as an answer but as another layer of uncertainty. Speculation naturally follows. If an object can endure for billions of years with preserved volatiles, does that mean countless more wander unseen, crossing interstellar space with hidden reservoirs of chemistry? If so, the galaxy may be filled with frozen archives of planetary history, drifting silently until chance brings them into reach. If not, and Atlas is instead a younger outlier, then we must ask why our first few detections have all been so unusual. Either conclusion reshapes expectations, but neither can be confirmed. The very act of trying to measure such vast timescales tests the limits of human imagination. We can say billions of years with ease, but comprehending what that span means for a fragile body of ice and dust is another matter. Civilizations rise and fall in mere centuries. Species appear and vanish in millions. Stars themselves live and die in billions. For a comet to survive across those spans is almost absurd, yet Atlas may be exactly that. A relic older than Earth, older than the Sun, still intact enough to confound us. As Atlas recedes into the dark, its age will remain unresolved. Models will continue to explore scenarios, weighing survival against chemistry, velocity against origin. But the numbers will never converge on certainty. Age, instead of grounding the object in time, becomes another unanswerable question, stretching our understanding to its limits. Atlas may be ancient beyond comprehension, or younger than its path suggests. Either way, its presence reminds us that time itself is a force as mysterious as space, and that some objects carry histories so vast they resist all attempts at reconstruction. One of the most striking things about 3i Atlas is not just what it shows, but what it does not. Astronomers are trained to listen for signals, to search for patterns, to find meaning in data that seems faint or incomplete. With Atlas, there are silences that are louder than noise, absences that draw attention precisely because they resist explanation. For an interstellar comet, every detail is precious. Every photon, every line in the spectrum, every faint deviation in motion carries the potential to teach us something about where it came from and what it is made of. But in Atlas's case, the things that should have been obvious, the signatures that should have been easy, remain absent or distorted. That silence itself has become one of the most puzzling aspects of the entire encounter. The first silence lies in the expected water signal. Comets brighten and vent water as they approach the sun. Their spectra light up with lines of hydroxyl and oxygen, clear markers of H2O breaking apart under solar radiation. Atlas, however, carried only faint traces of water, almost vanishing compared to the overwhelming carbon dioxide signature. The silence of water lines was startling. This wasn't just an absence by degree, but a suppression so strong it contradicted decades of cometary science. Observatories strained to confirm whether even the tiny signals they did see were real. When the instruments confirm that water is present at levels so low that it can barely be distinguished from noise, the silence itself becomes the dominant feature. Another silence comes from non-gravitational acceleration. In many comets, outgassing produces small but measurable deviations in trajectory. These are not mysteries, they are predictable consequences of asymmetric venting. But with Atlas, despite its vigorous coma and CO2-driven activity, the orbit remained too clean. If the gas was escaping so strongly, there should have been subtle pushes and pulls altering the path. observers searched for them in the Duality, expecting tiny wobbles that would confirm the physics at work. Instead, the measurements stubbornly adhered to pure gravity. If deviations were present, they were below detection thresholds. A body this active should have spoken through its trajectory, but instead the silence of motion echoed. The light curve also carried its own version of silence. While it displayed irregular spikes and plateaus, it failed to reveal clear periodicity. Most comets eventually disclose a rotation period, a rhythm that allows astronomers to connect brightness changes to physical spin. Atlas withheld that rhythm. The absence of a stable signal made it impossible to confirm whether it was rotating predictably or tumbling chaotically. Observers waited for the data to resolve into a pattern, but the silence persisted. A comet that should have been telling us about its rotation instead left the story unfinished. Dust signatures added more puzzles. Typical comets display characteristic patterns of dust release, with tails evolving in ways that reveal grain size and distribution. In Atlas, the dust production seemed inconsistent, sometimes too weak for the gas output, sometimes unexpectedly strong. Features that should have revealed themselves in polarization data were muted, almost invisible. The silence of dust parameters meant that interpretations wavered, unable to lock onto a clear explanation. Was the dust unusually fine? Was it clumping in ways that suppressed signatures? Without clear answers, the absence itself grew louder. Radio searches provided another layer. After Oumuamua sparked speculation about artificiality, radio telescopes were quick to listen for signals from subsequent interstellar visitors. Not because astronomers expected to hear anything, but because the opportunity could not be wasted. Atlas was no exception. Observations were made, frequencies scanned, silence confirmed. The lack of any artificial emission was expected, but even here, the silence spoke. It closed doors on the most exotic possibilities while highlighting how natural explanations, however strained, remained our only path forward. Yet the thought lingered. If it were artificial, perhaps silence would be the very point. The broader silence lies in comparison. Every comet observed in our system has a context. Their silences are filled by the thousands of others that behave similarly. Outliers exist, but they can be measured against the background of a population. Atlas has no such comfort. Its silences cannot be explained away by pointing to patterns among siblings. It has no siblings here. The absence of a population to compare against makes every missing signal feel louder. We cannot say, this is unusual but not unprecedented, because precedent does not exist. The silence of context isolates Atlas, forcing us to wrestle with its anomalies alone. Even the attempt to backtrack its origin produces silence. Orbital integrations fade into uncertainty after only a few million years, dissolving into noise against the galactic background. We cannot trace it to a parent star, cannot reconstruct a birthplace, cannot identify a system where its chemistry might make sense. That silence of history may be the loudest of all. It drifts into our telescopes bearing secrets we cannot unlock, not because the data is poor, but because the trail itself has been erased by time. For astronomers, silence can be as instructive as noise, but only if interpreted correctly. With Atlas, interpretation has proven elusive. Water silence suggests exotic chemistry, but how exotic is too exotic to be natural? Orbital silence suggests symmetry in venting, but how symmetrical can chaotic outgassing truly be? Rotational silence suggests tumbling, but how can tumbling remain hidden in so much data? Each silence leads to speculation, but none to certainty. Comparisons with Oumuamua and Borisov underscore the irony. Oumuamua was filled with silences, no coma, no detectable outgassing, no clear explanation for its acceleration. Borisov was noisy by comparison, a comet whose activity shouted its water-rich chemistry. Atlas falls somewhere between, noisy in its CO2 but silent in everything else. The silence it carries feels selective, targeted, as though it withholds precisely the signals we most need to resolve its mysteries. Of course, this is projection, nature has no intent, but the pattern is striking nonetheless. These silences do not just frustrate astronomers, they reshape how we think about interstellar objects. If 3 detections can already produce so much contradiction, one elongated and silent, one conventional and noisy, one chemically extreme but otherwise muted, then what will 100 reveal? Will the silences fill in, producing patterns, or will they multiply, showing us that the galaxy is stranger than we imagined? Atlas suggests the latter, that silence may be the rule rather than the exception. For now, the loudest message is that the absence of expected signals is itself information. The silence of water points to unusual chemistry. The silence of orbital deviations points to symmetry or suppression. The silence of rotation points to irregular dynamics. Each silence leaves us unsatisfied, but each also hints at truths beyond our models. Atlas may never explain itself fully, but its silences ensure that it will not be forgotten. In the quiet gaps between data points, in the missing signals where certainty should have lived, we are forced to confront the limits of our knowledge. And so Atlas continues outward, carrying with it a silence that is not emptiness but complexity. Observatories track its fading light, instruments record the last measurable signals, and in the background remains the louder message of what is not there. A comet that should have spoken clearly through water, dust, motion and rotation instead speaks through silence. It is a silence that demands attention, a silence that refuses to be dismissed, a silence that reminds us that the universe often withholds the very signals we most desire. Astronomy thrives on patterns. The night sky is filled with regularities, and those regularities allow prediction. Planets orbit in ellipses, comets brighten along repeatable curves, stars pulsate with measurable rhythms, galaxies rotate according to their mass distributions. With enough data, the patterns fall into place, and once in place, they can be projected forward. That ability to predict is what separates science from description. It is what makes astronomy not just an act of observation, but an act of understanding. When a comet is discovered, models quickly forecast how bright it will become, when its peak will occur, what kind of activity it will show, and how its tail will evolve. The confidence is not misplaced. Thousands of comets have behaved exactly as expected. Atlas, however, has consistently refused to align with these predictions. Every attempt to impose a pattern has been met with defiance. Instead of clarifying, each model collapses under the weight of new contradictions. Brightness was supposed to follow a simple path. As it neared the sun, the curve should have risen steadily, modulated only by rotation or small outbursts. Predictions were made based on its early measurements, forecasts that Atlas would brighten in certain steps and reach expected magnitudes by perihelion. Those forecasts failed. At times, Atlas outperformed them, shining more strongly than the models allowed. At other times, it dimmed inexplicably, falling below projections. The pattern that should have stabilized into a curve instead wavered like noise. Predictions that should have been reliable became useless, forcing constant recalibration. Gas production should have revealed another predictable sequence. Solar heating increases, volatiles sublimate, gas release accelerates, ratios shift in measurable ways. Instead, the CO2 dominance remained fixed, ignoring the expectation that water would eventually rise to take over. Forecasts of water activity ramping up failed to materialize. Predictions of changing ratios collapsed in the face of flat results. Each silence where a signal should have appeared became another broken expectation, another pattern that refused to form. Rotation should have been the key to bringing order out of irregular brightness. A nucleus spins, its active regions vent, the brightness fluctuates with a period that can be extracted from the data. Observers searched for that rhythm, expecting the irregularities to resolve into a repeating signal once enough data was collected. Instead, the fluctuations remained inconsistent. Periods that appeared briefly disappeared with further monitoring. Fits that worked for a handful of nights collapsed when the dataset doubled. A pattern that should have been inevitable dissolved every time it seemed within reach. Dust tails also normally follow predictable paths. Solar radiation pressure shapes their curvature, while gas flows shape ion tails. Models of particle size and emission rates allow simulations that match observed structures. With Atlas, the tails sometimes aligned, but at other times deviated in ways the models could not reproduce. Features appeared at unexpected angles, persisted longer than they should, or faded too quickly. Predictions made from one night's images failed when applied to the next. Instead of regular evolution, the tail behaved as though driven by unseen forces. Even the trajectory itself, though stable under gravity, became a source of broken expectations. If outgassing was as vigorous as the coma suggested, deviations from pure gravitational motion should have been measurable. Predictions of small accelerations were made, only to be met with silence. The lack of deviation became a defiance of the expected, another pattern that refused to appear. The orbit followed the math of gravity more cleanly than the activity should have allowed. The contradiction grew sharper with every precise measurement that confirmed both vigorous outgassing and absent acceleration. These failures of prediction accumulate into more than annoyance. They undermine confidence in the models themselves. Cometary science is built on decades of pattern recognition. When a new object refuses to align, the instinct is to assume missing data, temporary anomalies, or unusual conditions. With Atlas, however, the refusal has been persistent. Every property we try to forecast ends up wandering away from expectation. It is not a matter of one anomaly, but of many, layered across chemistry, brightness, dust, rotation, and motion. The cumulative effect is that Atlas becomes unpredictable by nature. This unpredictability challenges the very idea of classification. To call Atlas a comet suggests behaviour that fits within cometary norms. To call it interstellar implies it should behave like other interstellar examples. It does neither. Instead, it hovers between categories, borrowing features but discarding predictability. Predictions rely on comparison to past cases. With Atlas, comparisons only highlight the gaps. Oumuamua defied prediction in one way. Borisov fit expectations neatly. But Atlas combines traits of both and adds contradictions of its own. The attempt to predict based on precedent collapses when precedent is inadequate. The failure to find patterns also undermines communication. Scientists prefer to present results with confidence, to say not only what is happening but what will happen. With Atlas, the cautious phrasing of forecasts has been repeatedly undercut by reality. Predictions issued one week are contradicted the next. This forces humility, but also frustration. An object that cannot be predicted is an object that cannot be explained cleanly. It leaves astronomers presenting data without narrative, numbers without story, because the story keeps changing faster than it can be told. For theorists, the refusal of Atlas to settle into patterns becomes an opportunity and a burden. It invites new models, new frameworks that might accommodate irregular behaviour. Perhaps its nucleus is fractured internally, with activity venting in ways that shift unpredictably. Perhaps its surface crust is patchy, breaking and resealing in irregular cycles. Perhaps interstellar exposure has created chemistry that destabilizes in ways unfamiliar to us. Each possibility spawns simulations, and some match certain datasets, but none match them all. Every model built to explain one broken pattern eventually runs into another. The more they are tested, the more they fracture. The unpredictability also plays into speculation beyond conventional science. If Atlas refuses to follow patterns, could that mean it is not a natural body? Artificial explanations are rarely invoked seriously, but they persist at the edges. A brightness curve that refuses to stabilize, a trajectory that resists non-gravitational acceleration, a silence of water lines, all can be spun into narratives of design rather than nature. Few astronomers endorse this, but the lack of patterns leaves gaps that speculation rushes to fill. The louder the unpredictability, the harder it is to silence alternative interpretations. Yet even if Atlas is entirely natural, its defiance carries lessons. It may be showing us that interstellar comets exist in a broader spectrum of behaviours than we imagined. Our models are built on the narrow sample of solar system examples, shaped by one star's chemistry and history. If other stars produce comets with radically different internal structures, then our predictive frameworks will break when applied to them. Atlas may not be an exception, but an introduction, the first sign that our assumptions were too narrow. If so, the lack of patterns is not a failure, but a warning. Expect diversity. Expect unpredictability. Expect the galaxy to surprise. The persistence of unpredictability also shifts the focus of study. Instead of using Atlas to refine existing models, it forces us to ask how models themselves must change. Instead of fitting it into frameworks, we may need frameworks flexible enough to encompass objects that refuse to follow rules. This is a harder path, but a necessary one if interstellar surveys continue to find anomalies. Atlas shows us that the universe does not conform to our desire for neat predictions. It behaves as it does, and our task is to adapt. For now, Atlas remains case study in patterns that evade prediction. Its brightness curves defy forecasts, its chemistry ignores expectations, its dust-tails wander from models, its rotation hides, its trajectory resists non-gravitational deviations. Every domain where prediction should bring order has instead collapsed into contradiction. It is an object that teaches by refusing to be taught, that speaks by defying the language of patterns we rely on. As it recedes into the outer system, the failure of prediction will remain its legacy. Astronomers will continue to analyse its datasets, searching for hidden rhythms, trying to salvage order from the irregularity. Perhaps some patterns will eventually emerge, buried in noise, but even if they do, the broader message will not change. Atlas showed us that our ability to predict has limits, that not all comets behave predictably, and that interstellar wanderers may carry irregularities too complex for our current tools. The refusal to settle into patterns is not absence but presence, not failure but lesson. Atlas evades prediction not because it is meaningless, but because meaning lies beyond what our present models can see. When astronomers confront contradictions in their data, the next step is to ask whether the strangeness comes from something hidden in the object itself, or from something hidden in our own assumptions. A comet that behaves unlike any comet we have ever seen can be explained in two broad ways. Either it carries mechanisms we do not yet understand, internal processes that drive its unusual chemistry, brightness, and motion, or our frameworks for interpreting such data are flawed, built on assumptions that do not apply beyond the narrow domain of our solar system. With 3i Atlas, both possibilities are in play. It could be revealing hidden mechanisms within its nucleus, or it could be exposing hidden assumptions in our science. The challenge is that the evidence seems to support both, depending on where you look. Consider the dominance of carbon dioxide in its spectrum. One interpretation is that Atlas hides a mechanism by which CO2 becomes preferentially vented while water remains trapped or suppressed. Perhaps its nucleus has layers structured in a way that channels CO2 to the surface. Perhaps fractures run through volatile-rich zones that selectively release one component. Perhaps unknown chemical processes, triggered by cosmic ray exposure during interstellar travel, altered its stratigraphy to produce this imbalance. If so, then the anomaly reflects a hidden mechanism within the comet itself, a property we had not encountered before but that is nevertheless natural. But another interpretation is that the imbalance reflects hidden assumptions in our expectations. We assume that water should dominate because water dominates comets in our system. But maybe that is a local bias. Maybe other systems produce comets where CO2 is abundant and water is rare, and we simply never accounted for that possibility because our models were built too narrowly. In that case, the anomaly is not in Atlas, but in us. We expected water because our frameworks assumed universality where none exists. The same question applies to brightness variations. Are the irregular spikes and dips the product of hidden mechanisms, such as internal fractures that vent unpredictably, or surface crusts that collapse sporadically? If so, then Atlas is teaching us about the physical complexity of cometary nuclei, revealing processes too messy to model cleanly. Or are the irregularities the result of hidden assumptions in how we interpret light curves? We assume fluctuations correspond to rotation or activity bursts, but perhaps interstellar comets behave differently. Perhaps their surfaces scatter light in ways that break the patterns we expect, making our interpretive frameworks inadequate. Trajectory offers another example. A comet this active should experience measurable non-gravitational accelerations. Atlas has not. One explanation is a hidden mechanism. Maybe its venting is unusually symmetric, balancing forces in a way rare among comets. Another is a hidden assumption that we expect asymmetric venting because that is what we see locally, but perhaps in interstellar comets, symmetry is more common. Or perhaps our models for how gas jets impart force are oversimplified, and Atlas is exposing that weakness. Even its survival raises the same duality. A body that may have been wandering for billions of years should not be so active, so volatile rich. One explanation is a hidden mechanism of preservation, such as insulating crusts or self-regulating processes that protect interior ices. Another is a hidden assumption that survival over such timescales is unlikely. But maybe our assumptions about fragility are overstated. Maybe far more objects survive than we imagine, and Atlas is simply proving that possibility. This dual framing, mechanisms or assumptions, runs through every anomaly. When something refuses to fit, we can either expand the science to include new processes, or we can step back and question whether we built the science on biased premises. In practice, both often happen together. Discoveries expose new mechanisms and force re-evaluations of assumptions, but Atlas highlights the tension with unusual sharpness, because its anomalies pile up so consistently across multiple domains. If it were just chemistry, or just brightness, or just motion, we could isolate the hidden factor. But when all three resist explanation, we are forced to wonder whether the true problem lies deeper. One reason assumptions may be failing is the narrowness of our sample. Nearly everything we know about comets comes from our own solar system. We assume that what is true here applies everywhere. When the first interstellar visitors arrived, we expected them to behave like our own comets. Borisov did, and we were reassured. Oumuamua and Atlas did not, and the reassurance evaporated. The problem may not be with them at all, but with our assumption of universality. The galaxy may produce comets with far wider diversity than we ever imagined. If so, then Atlas is not strange. It is simply different, and our frameworks were too limited to account for difference. On the other hand, hidden mechanisms remain plausible because we know so little about how interstellar travel alters small bodies. Billions of years in deep space may create processes we have never modelled. Mechanisms of crust evolution, fracture propagation, or volatile segregation that are invisible in solar system comets. Atlas may be behaving according to rules we have not yet discovered. In that case, our assumptions are not wrong, merely incomplete, and Atlas is expanding them by revealing new physical truths. The tension between these two views is not easily resolved. Both may be correct. Atlas may hide mechanisms we cannot see, while also exposing assumptions we did not question. In that sense, it serves as a mirror, showing both the limits of our knowledge about nature and the biases we bring to interpreting it. It is a reminder that anomalies are not just about the object under study, but about the framework used to study it. For astronomers, this is both frustrating and exciting. Frustrating because it denies closure, leaving questions unresolved. Exciting because it means discovery lies ahead, whether in the form of mechanisms waiting to be uncovered or assumptions waiting to be discarded. Atlas may not give us the answers directly, but it forces us to recognise that the answers we thought we had may not be enough. The longer its data is studied, the clearer it becomes that the contradictions will not dissolve easily. Each new measurement forces a choice between invoking hidden mechanisms or revising hidden assumptions. Neither path is comfortable, and both require humility. Mechanisms admit ignorance of natural processes, assumptions admit bias in human frameworks. Atlas demands both, reminding us that science progresses not only by adding data, but by confronting what data reveals about our limitations. And so Atlas continues to move outward, leaving behind not a neat story, but a series of questions that press in two directions at once. If its behaviour is the product of hidden mechanisms, then the cosmos is richer and more complex than we imagined. If its behaviour is the product of hidden assumptions, then our models are narrower and more fragile than we believed. In both cases, the lesson is the same. The more we study, the less certain we become, not because knowledge is failing, but because knowledge is expanding into regions where certainty cannot yet reach. Every observation of 3i Atlas has depended on the reach of our instruments. Without telescopes, it would have passed unseen, just another interstellar traveller lost to the dark. Detection itself was an achievement, the product of careful surveys scanning the sky for transient motion. But from the moment it was discovered, the struggle began to push our telescopes to their limits. Atlas is not bright enough to reveal itself in obvious detail, not close enough to resolve clearly, not stable enough to produce easy signals. What we know comes from photons stretched to their breaking point, instruments strained to capture data at the edge of sensitivity. Each data set reminds us not only of what Atlas is, but of what we cannot yet see. From the earliest images, the problem was apparent. Atlas appeared as a faint speck against the background of stars, a smudge barely distinguishable from noise. Only by stacking exposures and applying motion filters could astronomers isolate it. That process introduced uncertainties, smoothing details, merging features that might otherwise reveal subtlety. Even at discovery, the limits of resolution shaped what could be learned. Brightness was measurable, but structure was blurred. The nucleus itself remained hidden behind the coma, an unresolved point no telescope on Earth could separate. Spectroscopy faced similar limits. Instruments like the James Webb Space Telescope could capture emission lines, but only by stretching integration times and filtering out overwhelming background. The signals of CO2 were clear, but waterlines hovered at the edge of detection, barely distinguishable from noise. Uncertainty bands widened because the lines were faint. The result was confidence in CO2 dominance, but little clarity about absolute abundances. The telescope delivered what it could, but the object's faintness limited precision. In those limits, interpretation grew shaky, and every conclusion carried caveats. Ground-based observations of dust faced atmospheric interference. Adaptive optics helped, but even the best facilities could not produce images sharp enough to resolve fine structures in the coma. Jets, fans, and filaments that might reveal the geometry of activity remained smeared. What looked like diffuse emission could in reality be structured, but the telescopes could not confirm it. Predictions about symmetry or asymmetry rested on blurred images, leaving uncertainty intact. Rotation was another casualty of instrumental limits. Brightness variations were measurable, but only faintly above noise. Small telescopes struggled to track the irregularities across nights, producing incomplete curves. Larger facilities could capture higher precision, but competition for observing time-limited coverage. The result was fragmented datasets, stitched together with gaps that left rotation models ambiguous. Atlas may have been broadcasting its spin, but our instruments were not sharp enough, frequent enough, or consistent enough to decode it. Even orbital measurements depended on telescope precision. Tracking a faint moving object across the sky requires accurate astrometry. Atlas's faintness made that difficult. observatories had to stretch exposures, sometimes blurring position slightly, sometimes introducing systematic errors. While the orbit was eventually confirmed with high accuracy, the early stages carried uncertainties larger than desirable. If there had been non-gravitational deviations, they might have been missed in the noise. The silence of acceleration may reflect not only the object's behaviour, but the limitations of detection. Infrared instruments could, in principle, measure the nucleus's thermal emission, offering constraints on size. But Atlas was too faint for most facilities. Even space telescopes struggled, with fluxes near the edge of sensitivity. What data was captured came with broad error bars, leaving room for conflicting interpretations. The result was a size estimate spanning an order of magnitude, less a measurement than a guess constrained by instrumental reach. Comparisons to previous interstellar visitors highlight how much our telescopes shape what we know. Oumuamua was faint, featureless, and beyond resolution, forcing us to interpret from light curves alone. Borisov, by contrast, was brighter, closer, and more easily studied, allowing high confidence measurements. Atlas fell in between, bright enough to measure but faint enough to strain precision. The differences in what we know about each object come less from what they are, and more from what our telescopes could capture. Atlas is not only a comet, it is a test of technological reach. The limits extend beyond raw sensitivity. Observing time is finite, and telescopes must divide their attention among countless targets. Atlas competed with supernovae, exoplanets, galaxies, and other comets for resources. Each observation was a compromise. A longer integration here meant a shorter one elsewhere. Gaps in coverage reflected the constraints of scheduling as much as the object itself. In those gaps, crucial transitions may have been missed. The irregularities of brightness, the timing of outbursts, the evolution of the coma, all may have hidden signals lost between observation windows. Even when data was captured, calibration errors introduced noise. Atmospheric interference, detector limitations, cosmic ray hits, all chipped away at precision. Astronomers worked tirelessly to correct for them, but corrections themselves add uncertainty. In the end, the story of Atlas is not just its own. It is also the story of the instruments straining to measure it. For astronomers, these limits are not new. Every object beyond Earth is studied at the edge of what telescopes can reveal. But Atlas amplifies the issue because it is unique. We cannot wait for another pass, cannot compare with a twin, cannot return to it later. The fleeting opportunity magnifies the frustration of limits. Each photon wasted is a piece of history lost forever. Each gap in coverage is a missed chance to learn from an object that will never return. The lesson is that discovery often outpaces capability. We found Atlas because our surveys are sensitive enough to detect faint transients, but studying it required instruments more powerful than we currently possess. This mismatch between detection and analysis creates a gap. We know it exists, we can measure some properties, but the full picture remains hidden. The object itself is beyond us, not in principle, but in practice. If our telescopes were larger, sharper, and more numerous, many of the mysteries might dissolve, but they are not, and so the mysteries remain. This realization drives the urgency for future surveys. Projects like the Vera Rubin Observatory promise to expand detection and tracking. Space telescopes with greater infrared sensitivity promise sharper chemical insights, but Atlas will not wait for them. It came too soon, slipping past before the next generation of instruments came online. Its mysteries are now frozen in imperfect data, forever limited by the tools of its time. Future comets may be captured with greater clarity, but Atlas will remain defined by what our telescopes could not do. For some, this is the most frustrating truth. The object itself may not be unknowable. It may not be an enigma in principle. Its secrets might have been revealed if only our telescopes were larger, if only our coverage were denser, if only our instruments were sharper. The barrier is not cosmic, but technological. And that makes the mystery sharper. because it implies that the answers exist just beyond reach, visible in principle but invisible in practice. Yet even in this frustration lies progress. Each limit revealed by Atlas highlights where instruments must improve. Each unanswered question becomes a goal for future missions. The silence of waterlines pushes for more sensitive infrared telescopes. The ambiguity of rotation pushes for denser photometric coverage. The uncertainty of size pushes for higher resolution imaging. Atlas is not just an object, it is a guide, showing us the weaknesses in our observational arsenal. As it recedes, telescopes will continue to stretch to follow it, though each night it grows fainter, each data set thinner. The limits will tighten until it disappears entirely, swallowed by distance. What remains will be the record of what we could see and the echo of what we could not. The limits of our telescopes define the limits of our knowledge. Atlas reminds us that the universe often offers puzzles not because they are unsolvable, but because we are not yet ready to solve them. Science thrives on consistency. Independent measurements from different instruments, repeated observations across different observatories, overlapping analyses by different teams. When they converge, the confidence grows. Contradictions are not supposed to multiply as the dataset expands. If anything, anomalies usually fade under weight of evidence, revealing themselves as calibration issues or limited perspectives. With 3i Atlas, the opposite occurred. The more telescopes observed it, the more papers were written, the more spectra were collected, the more contradictions piled up. Data that should have converged instead fractured, creating an object defined not by clarity but by discord. The first contradiction arose in brightness. Some observers reported that Atlas brightened faster than models predicted, outshining expectations as it approached the Sun. Others, using different filters or calibration methods, found it dimmer, underperforming forecasts. Even when accounting for instrument sensitivity, the divergence remained too large. Was Atlas unusually active, or was it sluggish? The answer depended on which dataset you trusted. Photometry, that should have been straightforward, became a landscape of contradictions. Spectroscopy compounded the problem. Space-based instruments like James Webb revealed strong CO2 emission, with waterlines barely visible. Ground-based observations, however, sometimes suggested higher water activity than the space data implied. The ratio of carbon dioxide to water swung, depending on method, wavelength, and calibration. Some teams argued that water was nearly absent, others that it was suppressed but still significant. The contradiction grew sharper because neither side was careless. The data was solid, the technique sound. The object itself seemed to change depending on how you looked at it. Rotation added another layer. Photometric monitoring by one group suggested a rotation period of around 8 hours. Another group, analysing the same time frame but with different filters, proposed chaotic tumbling with no stable period. A third group found hints of a longer rotation, close to 20 hours. Each interpretation explained part of the light curve but failed with another segment. Instead of resolving the nucleus's spin, the data split into mutually incompatible models. A comet should not spin 3 ways at once, yet the measurements left all 3 plausible. Dust production estimates contradicted one another just as sharply. Some analyses concluded that Atlas released surprisingly little dust compared to its gas output, implying an unusually clean coma dominated by volatiles. Others measured dust production rates consistent with typical comets, suggesting the opposite. Still others suggested bursts of fine dust that spiked brightness temporarily but did not persist. Each conclusion was based on real observations, yet when combined, they painted an impossible picture. Atlas both dusty and dust-poor, both stable and bursting. The contradictions even extended to its trajectory. Some early astrometric data hinted at tiny deviations from pure gravity, raising the possibility of non-gravitational accelerations. Later, more precise data sets erased those signals, showing a clean hyperbolic orbit with no measurable perturbations. Which was true. Did Atlas vent symmetrically enough to cancel accelerations? Or were the early deviations real but smoothed out by later coverage? The data could not agree with itself. Infrared observations meant to constrain size ended up broadening the contradictions. Depending on assumptions about albedo and thermal properties, analyses produced diameters ranging from a few hundred meters to several kilometers. Some datasets leaned toward the smaller end, others the larger. The contradictions were not just in interpretation, but in the flux values themselves, which sometimes overlapped poorly between instruments. A body cannot be both small and large, yet the data supported both. Even within single datasets, contradictions lurked. The same light curve could be fitted to multiple rotation periods, each producing plausible results. The same spectrum could be modelled with different dust-to-gas ratios, each explaining part of the signal, but not all. The contradictions were not simply between instruments or teams, but within the very act of measurement itself. For astronomers, such contradictions force uncomfortable questions. Are the instruments miscalibrated? Are the models flawed? Or is the object itself unstable, changing faster than measurements can keep up with? Each possibility carries different implications. Calibration issues would undermine confidence in the data. Model flaws would expose hidden assumptions. Rapid variability would make Atlas more unusual still. None of these explanations dissolve the contradictions. They only shift responsibility from data to framework to object. Comparisons to previous interstellar visitors highlight the difference. Oumuamua produced contradictions too. Its trajectory suggested outgassing, but no gas was detected. But those contradictions were focused, a single anomaly debated endlessly. Borisov, by contrast, produced consistent data across instruments, reinforcing its classification as a conventional comet. Atlas combined the worst of both, contradictions sprawling across brightness, chemistry, dust, rotation, and trajectory, leaving no single stable core of agreement. The contradictions also affect interpretation of origin. If water is nearly absent, Atlas must have formed in a CO2-rich, water-poor environment. If water is present at suppressed levels, then perhaps interstellar processing reshaped it. If dust is scarce, the nucleus may be unusually icy. If dust is abundant, it may resemble solar system comets more closely. Each contradiction generates mutually exclusive narratives. Atlas cannot be placed cleanly into any one origin story, because the data itself refuses alignment. This proliferation of contradictions challenges not only the study of Atlas, but the practice of astronomy itself. Science relies on the assumption that independent measurements converge on truth. When they do not, the process stalls. Atlas forces recognition that sometimes nature presents itself in ways that produce contradictory data not because of error, but because of complexity. A body venting irregularly, fragmenting unpredictably, scattering dust unevenly may produce datasets that look inconsistent while all being correct. Contradiction becomes a property of the object, not a failure of observation. For theorists, this is both nightmare and opportunity. Nightmare because it denies clear conclusions, leaving uncertainty where answers should be. Opportunity because contradictions hint at new physics, new chemistry, or new processes waiting to be discovered. If Atlas resists convergence, perhaps it is because our frameworks are too narrow, our models too rigid. Contradictions become guides, pointing toward what must change. Speculation inevitably fills the gaps. Some argue that contradictions suggest artificiality, that only a constructed object would produce such selective signals. Most dismiss this, noting that natural complexity is sufficient, but the contradictions leave room for those interpretations, feeding imagination precisely because they deny closure. Atlas becomes a canvas for speculation, not by intention, but by the refusal of its data to agree with itself. The most sobering realization is that the contradictions may never resolve. Atlas is already fading, receding into the dark where no telescope will follow. The data sets we have are all we will ever have. No new measurements will appear to break the stalemate. The contradictions will persist in the archives, debated by future astronomers, reanalyzed with new models, but never fully resolved. Atlas will remain an object defined by data that contradicts itself, a puzzle frozen in incompleteness. And yet within that incompleteness lies its greatest value. Contradictions force humility. They remind us that data is not truth, that measurement is not meaning, that science advances not by avoiding contradiction, but by confronting it. Atlas embodies this lesson more sharply than any comet before. It refuses convergence, refuses closure, refuses to be explained away. It forces us to admit that sometimes the universe does not give consistent answers, not because we failed, but because complexity itself resists simplification. As Atlas disappears into interstellar space, the contradictions will remain, echoing in papers, models, and debates. Each dataset will continue to argue with the others. Each interpretation will continue to clash. The contradictions will not fade, but they will endure as reminders. The universe is not obliged to make sense on our terms. Sometimes the data contradicts itself because reality is messier than we allow. Atlas is a messenger of that truth, carrying not clarity but contradiction, not simplicity but complexity, not agreement but discord. The promise of science is that answers build foundations. Each discovery closes one door and opens another, but the doors open in progression, leading toward deeper clarity. Questions multiply, but they multiply on top of stable knowledge. The orbit of Mercury puzzled astronomers, but the resolution through general relativity created more profound inquiries about space and time. The discovery of DNA's structure raised countless new problems, but the foundation of molecular inheritance was secure. With Atlas, the opposite seems to be happening. Each time astronomers think they have secured an answer, it immediately generates not stability, but contradiction. Instead of foundations, it produces fractures. Each answer creates more questions, and those questions spread in every direction. Take the answer about its interstellar nature. Orbital eccentricity greater than 1 proves it is unbound from the Sun, confirming it as the third known interstellar object. That is an answer, simple and undeniable. But from that answer flows a torrent of questions. Where did it come from? How old is it? What system ejected it? How common are such visitors? Each of those questions splinters further, and none yields stable resolution. The answer that should have provided clarity instead multiplies uncertainty. Consider the chemistry. The James Webb Space Telescope confirmed strong carbon dioxide emission. That is an answer. It tells us the comet is dominated by carbon dioxide, with water suppressed to levels rarely seen. But immediately the questions expand. Why CO2? What formation zone produces such a ratio? Was water depleted by interstellar radiation, or was it scarce from the start? Does this chemistry represent an outlier or a broader class of interstellar comets? The single answer about composition blossoms into more questions than it resolves. Brightness variations offer another case. Observers measured irregular fluctuations, inconsistent with smooth models. That is an answer. The nucleus is not rotating simply, or activity is variable. But the answer breeds questions. Is it tumbling? Is it fragmenting? Are the variations from jets, dust, or geometry? Each possibility leads to new inquiries about structure, dynamics, and behavior. The answer that there is variability only reveals how little we understand the cause. Trajectory follows the same pattern. Measurements confirm a hyperbolic path with excess velocity of 61 kilometers per second. That is an answer, precise and repeatable. Yet it raises questions about origin, ejection mechanisms, and galactic history. How does an object achieve such speed? Did multiple stellar encounters accelerate it? Was it born in a system unlike ours? Could selection bias make fast objects more likely to be detected? Each answer in motion births a web of questions about history and probability. Even nucleus size, one of the most basic properties, illustrates the cycle. Estimates ranging from a few hundred meters to several kilometers show that we cannot pin it down. That contradiction is itself an answer. The nucleus cannot be measured cleanly with current data. But that answer provokes questions. If it is small, how did it survive interstellar travel? If it is large, why is its water activity so weak? Why do different methods produce such divergent results? Instead of resolving size, the answer creates competing scenarios, each generating more questions than the last. The same occurs with dust. Some datasets suggest dust-poor activity, others dust-rich bursts. That is an answer of sorts. The coma is not simple, but it raises questions about particle size, ejection efficiency, and fragmentation. Is the dust unusually fine, unusually reflective, or unusually transient? Does the dust signal contradict or confirm the gas ratios? Each interpretation demands new questions about processes we do not yet model. The pattern is relentless. Every domain of study offers a result that refuses closure. The answers pile up, but instead of reducing uncertainty, they expand it. Atlas becomes not a source of clarity, but a factory of questions, generating them faster than science can contain. The more we measure, the less we settle, because each answer leads outward into contradictions and complexities. For astronomers, this inversion of expectation is disorienting. The normal rhythm of discovery is absent. Instead of narrowing possibilities, Atlas broadens them. Instead of stabilizing models, it destabilizes them. Each telescope that observes it adds more data, but the data only multiplies questions. The object becomes harder to explain, not easier, as the dataset grows. It is the opposite of what science promises, yet it is precisely what nature has delivered. The broader implication is that interstellar objects may not conform to the tidy narrative of answers leading to clarity. Perhaps their value lies in producing questions, in forcing recognition of diversity beyond expectation. If every visitor we find multiplies questions rather than reducing them, then the lesson is that the galaxy is more complex than models can yet hold. Answers do not settle, they destabilize. And in destabilization lies progress. Comparisons highlight this inversion. Oumuamua's lack of coma answered the question of activity, but that answer birthed endless debate about what drove its acceleration. Borisov's conventional activity answered the question of interstellar comet chemistry, but that answer raised new questions about why it was so typical while Oumuamua was so strange. Atlas's CO2 dominance answered the question of composition, but that answer launched dozens of new inquiries about formation and survival. Each interstellar object has followed the same pattern. Answers expand uncertainty instead of shrinking it. The persistence of this pattern suggests a deeper truth. Perhaps we expected too much clarity from too few data points. 3 interstellar visitors cannot define a population. Each one is likely to appear anomalous until the sample grows large enough to reveal distributions. Answers that create more questions may simply reflect the inadequacy of small numbers. But until more are found, we are trapped in this cycle, where each answer destabilizes more than it secures. Speculation thrives in this environment. If every answer generates contradictions, some wonder whether the contradictions hint at artificiality. Natural bodies should converge toward explanation, the reasoning goes. If these do not, perhaps they are not natural. Most astronomers reject that conclusion, but the fact that the question persists reflects the depth of uncertainty. The failure of answers to resolve invites speculation, not because it is supported, but because the vacuum demands filling. For scientists, the discipline lies in resisting the temptation to force answers into premature closure. Atlas teaches that patience is required, that answers which generate more questions are not failures but opportunities. Each contradiction points toward the frontier of ignorance. Each unexpected ratio, each irregular light curve, each puzzling trajectory is a marker of where our models break. Progress may not come in closure, but in the recognition that closure is not yet possible. As Atlas fades, the cycle will not end. Papers will continue to analyse its data, producing answers about chemistry, size, dust, and motion. But each of those answers will continue to spawn questions. Questions that will not resolve until many more interstellar comets are observed. Atlas will remain an object defined by expansion of uncertainty, not contraction. It will be remembered less for what it told us than for how many questions it left in its wake. From the moment interstellar objects began to be discovered, the question of whether they are natural or artificial hovered in the background. Oumuamua was the first spark. Its lack of a coma, its unusual shape, its unexplained acceleration, and its rapid exit raised possibilities that went beyond natural explanations. While the consensus leaned toward natural processes, the debate left a mark. Borisov reassured astronomers by looking like a normal comet, behaving predictably, and displaying all the signs of a natural body. Then came Atlas, carrying a strange mix of normal and abnormal traits, leaving the question unsettled. Its chemistry, its velocity, its brightness fluctuations, its ambiguous rotation, its contradictory data, all combined to reopen the discussion that science could not quite close. The natural explanation is straightforward in outline. Atlas is a comet ejected from another star system, just as comets in our own system are occasionally ejected by giant planets. It wandered through interstellar space for millions or billions of years, altered by radiation, collisions and time, before finally drifting into our neighbourhood. Its unusual chemistry reflects the diversity of formation environments. Its contradictions reflect the limits of observation and the complexity of cometary physics. This explanation does not require anything extraordinary. It only requires accepting that the universe is richer and stranger than our small sample suggests. But the artificial explanation cannot be ignored, because the anomalies invite it. If Atlas were designed, what would that design look like? An object on a clean hyperbolic trajectory, disguised as a comet, might be indistinguishable from natural debris. A civilization wishing to send probes across interstellar space could exploit the camouflage of cometary appearance. Its unusual chemistry might be the byproduct of engineering rather than formation. Its lack of measurable, non-gravitational acceleration, despite vigorous outgassing, might indicate control rather than chaos. The thought remains speculative, but it persists because Atlas refuses to resolve into a neat natural story. The difficulty lies in deciding between these narratives. The evidence for natural origin is strong, but not definitive. The evidence for artificial origin is weak, but not dismissible. Every anomaly that challenges natural models adds weight to speculation. Every natural explanation that survives scrutiny pulls the debate back from the edge. The balance never settles. Atlas hovers in the middle, neither confirming nor denying, neither closing the door nor opening it fully. Consider the chemistry. A CO2 to water ratio so extreme could mean natural diversity, or it could mean deliberate construction with unusual materials, which is more likely. Natural explanations invoke unknown formation zones or interstellar processing. Artificial explanations suggest engineering. Both are possible, neither is provable. The same applies to trajectory. A speed of 61 kilometers per second fits rare but possible natural ejection scenarios. It also fits the needs of an engineered interstellar probe. Again, the data sits in the middle, interpretable both ways. Brightness variations raise similar ambiguity. Irregular fluctuations could result from chaotic tumbling, fragmentation, or uneven venting. They could also result from controlled modulation, intentional or otherwise. Dust production inconsistencies might reflect natural complexity, or they might reflect material release not intended to mimic comets perfectly. Each natural explanation carries plausibility, but each anomaly leaves a margin where artificial explanations linger. The problem is not lack of evidence, but the refusal of evidence to discriminate. Every dataset is compatible with natural scenarios stretched to their limits. Every dataset is also compatible with speculative artificiality. Neither explanation can be ruled out, but neither can be confirmed. We are left not with answers, but with indecision, unable to close the question. For scientists, the discipline lies in preferring natural explanations unless extraordinary evidence demands otherwise. Atlas has provided no extraordinary evidence, no radio signals, no structured emissions, no unambiguous markers of technology. But the accumulation of anomalies ensures the artificial question will remain alive, even if only at the fringes. It cannot be dismissed outright because the data does not allow complete closure. This ambiguity mirrors broader debates in science. When faced with anomalies, do we expand natural frameworks or allow for extraordinary hypotheses? With Atlas, the choice is sharper because interstellar visitors are so rare. Each one may be the only chance to confront the question in a generation. That scarcity makes the decision harder because the stakes feel higher. To dismiss artificial explanations prematurely risks missing the extraordinary. To embrace them without evidence risks undermining credibility. Atlas sits at the knife edge of that dilemma. Comparisons sharpen the picture. Oumuamua leaned toward artificial speculation because of its unexplained acceleration and lack of cometary features. Borisov leaned away because of its natural appearance. Atlas sits between them, presenting both cometary features and unexplained anomalies. It becomes a bridge between the two extremes, forcing the question back into focus. Was Oumuamua truly an outlier, or was it the first sign that interstellar visitors resist neat categorization? Is Borisov the exception or the rule? Atlas does not decide between these interpretations. It amplifies the uncertainty. Speculation about artificiality is not idle fantasy. It shapes the design of searches, the allocation of telescope time, the way scientists communicate results. Even if Atlas is almost certainly natural, the debate it provokes influences priorities. Radio observatories were deployed, frequencies scanned, silence confirmed. The absence of signals was itself data, showing that the artificial hypothesis was taken seriously enough to test. This caution reflects the depth of uncertainty. Natural models explain much, but not all. Artificial explanations cannot be confirmed, but neither can they be dismissed entirely. The indecision is amplified by the limits of observation. Atlas is faint, distant, and transient. We cannot resolve its nucleus directly, cannot sample its material, cannot track it indefinitely. We are left with indirect evidence that will always remain ambiguous. In this ambiguity, the natural or artificial question cannot be closed. Atlas will pass beyond reach before certainty can be achieved. The indecision will not resolve with new data, because no new data will come. For future interstellar visitors, the lesson is clear. We must be prepared to gather more decisive evidence, to resolve natural from artificial with sharper instruments. Atlas shows us how fragile the distinction is, how easily anomalies blur categories. If the galaxy sends, or releases, more objects into our view, we must have the tools to decide. Until then, Atlas remains suspended between explanations, a comet that could be natural, could be artificial, and gives us no way to choose, and so it moves outward, leaving the question unanswered. Natural or artificial, and why we cannot decide will remain its legacy. The inability to close that question reflects not failure, but the reality of science at the frontier. Answers are elusive, evidence is incomplete, and certainty is impossible. Atlas embodies that uncertainty, refusing to reveal its nature fully, leaving us caught between natural models stretched to their limit and artificial speculation we cannot confirm. When astronomers describe Atlas, they often reach for comparisons, models, and probabilities, trying to fit it into frameworks built from centuries of observation. But as the data accumulates, a different picture emerges, not of an object that reveals itself, but of one that reflects back our own uncertainties. Atlas has become less a comet to be explained, and more a mirror held up to our knowledge, showing us the limits of what we can claim to understand. Each measurement, each contradiction, each silence does not clarify the comet so much as it clarifies the gaps in our science. The mirror effect begins with expectations. We expect comets to follow patterns because thousands in our system do. We expect water to dominate chemistry because water dominates here. We expect brightness curves to be predictable because we have learned to model them. But when Atlas refuses, the refusal does not only describe the comet, it describes us, our reliance on assumptions, our dependence on patterns, our vulnerability when those patterns break. The uncertainty lies not only in the object, but in the framework we bring to it. This reflection extends to technology. Every telescope that strains to observe Atlas demonstrates not only its limits but ours. Instruments blur details, spectra fade into noise, brightness fluctuates beyond calibration. The comet itself may hold clarity, but the mirror shows us that our tools cannot reach it. We measure at the edge of sensitivity, interpret at the edge of precision, and the reflection reveals the fragility of our confidence. Atlas forces us to confront the reality that the cosmos is larger, faster, older, and stranger than our instruments are ready to handle. Even the debates about natural versus artificial origin reflect more about humanity than about the comet. The possibility of artificiality reveals our longing to find intelligence beyond Earth, our readiness to interpret anomalies through the lens of intent. The rejection of artificial explanations reflects our caution, our discipline, our insistence on naturalism unless forced otherwise. The uncertainty of Atlas is not only about chemistry and trajectories, it is about our psychology as scientists and as a species. It mirrors the tension between imagination and skepticism, between hope for discovery and fear of overreach. The mirror deepens when we consider survival. If Atlas is billions of years old, preserved across galactic timescales, then its endurance reflects the fragility of human timescales. Civilizations rise and fall in thousands of years. Species live for millions. Stars burn for billions. A comet drifting across the galaxy for longer than Earth has existed reflects back the smallness of our perspective, the brevity of our existence. The uncertainty of its age becomes the uncertainty of our place in time. The contradictions in its data sharpen the reflection. When brightness curves fail, when chemistry contradicts, when size estimates diverge, the mirror shows us the messiness of science itself. Data is not a window to truth, but a dialogue between observation and interpretation. Contradictions are not failures, but reminders that reality does not bend easily to our categories. Atlas reflects the uncertainty of science in practice, where answers are provisional, debates persistent, and clarity elusive. Comparisons to other interstellar visitors sharpen the mirror further. Oumuamua's silence mirrored our hunger for meaning and absence. Borisov's conventionality mirrored our relief when expectations held. Atlas mirrors something deeper, the instability of our frameworks themselves. It shows us that certainty is an illusion, that science at the frontier is less about answers and more about questions. Each of the three visitors reflects a different side of uncertainty, and together they form a pattern not of clarity, but of humility. The mirror does not only show limits, it shows possibilities. If Atlas's anomalies reflect our assumptions, then they point to where those assumptions can be challenged. If its contradictions reflect our models, then they point to where models can expand. If its silence reflects our instruments, then they point to where instruments must improve. In this way, the mirror is not discouraging but instructive. It shows us not that we cannot know, but that knowing requires change. The cosmic uncertainty reflected by Atlas is not a void but a frontier. It is the recognition that the universe is larger than our frameworks, that our knowledge is incomplete, that our confidence must be tempered. This uncertainty is not failure but progress. because it reveals where growth is possible. Atlas does not give us answers, but it gives us the gift of seeing our ignorance clearly. That is the first step toward overcoming it. For astronomers, this reflection is familiar. Every great discovery in history has held up a similar mirror. The realization that Earth is not the center of the universe reflected the limits of human perspective. The discovery of galaxies beyond the Milky Way reflected the limits of scale. The observation of cosmic acceleration reflected the limits of our understanding of gravity. Atlas continues this tradition, reflecting the limits of our assumptions about small bodies, chemistry, and interstellar diversity. The mirror of cosmic uncertainty is the mirror of science itself. But there is something sharper about Atlas. Its fleeting nature makes the reflection harsher. We cannot wait for another orbit, cannot send a spacecraft to catch it later, cannot resolve its mysteries with time. The reflection is brief, incomplete, frustratingly ephemeral. That makes the uncertainty more painful, because it cannot be resolved. The mirror flashes past, showing us our limits, then vanishes forever. The lesson is not only about ignorance, but about opportunity lost. This ephemerality also reflects the fragility of knowledge. How much of science depends on rare opportunities seized in time? A passing comet, a brief eclipse, a transient explosion. Missed observations cannot be regained. Atlas reflects the dependence of science on timing, resources, and luck. Its uncertainty is amplified by scarcity, by the knowledge that we will never see it again. The mirror shows us that cosmic uncertainty is not only about complexity, but about chance. Speculation fills the gaps left by the mirror. Artificiality, unusual formation zones, rare ejection events, all are projections of our imagination into the uncertainty. The mirror reflects this too, the way humans respond to ignorance with stories, models, and speculation. Atlas does not only mirror our knowledge, but our creativity, our biases, our hopes and fears. The uncertainty it reveals is not only cosmic, but human. As Atlas continues outward, the mirror remains. The data is archived, the contradictions preserved, the debates ongoing. Astronomers will revisit its records for decades, reinterpreting with new models, testing against future discoveries. Each reanalysis will see something new, not because Atlas has changed, but because we have. The mirror will continue to reflect our evolving frameworks, showing us not what Atlas is, but what we are becoming as we try to understand it. In the end, the mirror of cosmic uncertainty is not discouragement, but truth. Science does not move from ignorance to certainty in straight lines. It moves in circles, spirals, contradictions, and debates. Atlas reflects that reality more sharply than most objects. It shows us that the cosmos is not obliged to make sense, and that our role is not to demand certainty, but to embrace uncertainty as the path to deeper knowledge. When Oumuamua was first discovered, astronomers immediately leaned on familiar cometary frameworks to explain it. The lack of a visible coma was puzzling, but perhaps it was a rocky fragment, more asteroid than comet. The odd acceleration was harder, but outgassing, even if invisible, might account for it. Those explanations, while debated, came from the playbook of solar system science. When Borisov arrived, the situation seemed simpler. It looked and behaved like an ordinary comet, shedding gas and dust in ways we knew. The lesson seemed clear. Interstellar objects, while exotic, would ultimately align with our categories. With Atlas, that confidence has eroded. The lessons drawn from the first two visitors have proven less reliable than expected. What held true before does not apply now, and the rules we thought we were beginning to write dissolve under the contradictions. Oumuamua taught us to expect silence. No coma, no dust, no water lines, only faint brightness variations and unexplained acceleration. That lesson suggested interstellar objects might often be inactive, their volatiles depleted by long journeys. We imagined fragments hardened by cosmic rays, stripped of ices, more like inert rocks than comets. Atlas shattered that expectation. It is active, loudly so, with a coma dominated by CO2. The silence of Oumuamua is not the norm. Instead, Atlas reminds us that interstellar comets can be vigorous, noisy, and unpredictable. The lesson of silence no longer applies. Borisov taught us to expect familiarity. Its activity mirrored solar system comets, dominated by water and dust in familiar ratios. That lesson suggested interstellar comets would look like ours, simply displaced from other systems. The comfort of familiarity was strong, but Atlas dismantled that expectation as well. Its water suppression and CO2 dominance stand in sharp contrast to Borisov's normalcy. If Borisov reassured us that interstellar comets were familiar, Atlas warns us that they may not be. The lesson of similarity no longer applies. From Oumuamua, we also learned to be cautious with rotation models. Its brightness variations hinted at elongation and tumbling, but no clear period emerged. That lesson taught us that irregular shapes and complex spins might be common in interstellar bodies. When Atlas showed irregular light curves, we applied that lesson again. Yet the variations in Atlas do not behave the same way. Instead of consistent tumbling signatures, the fluctuations resist periodicity altogether, defying the frameworks we developed from Oumuamua. The lesson of irregular rotation does not map cleanly onto Atlas. It looks similar at first, but diverges on closer inspection. From Borisov, we learned to expect dust tails that align with models. Its coma and tail behave predictably, shaped by solar radiation and gas dynamics. That lesson suggested that despite interstellar origin, tail evolution would follow familiar patterns. But Atlas's tail sometimes conforms and sometimes deviates, persisting at angles or intensities that resist modelling. What we thought was predictable now appears conditional, as though Atlas is selectively choosing when to obey Cometary rules. The lesson of predictability does not carry forward. The speed of Oumuamua taught us that interstellar objects could arrive with modest excess velocities in the range of 20 to 30 kilometers per second. That framed our expectations for future visitors. Borisov reinforced it by carrying a similar velocity. The lesson was that interstellar speeds would fall within a certain range, plausible for ejection from planetary systems. Atlas discarded that too. Its 61 kilometers per second exceeds comfortable ranges, pushing into territory that feels improbable. The lesson of speed as ordinary no longer applies. The chemistry of Borisov taught us that interstellar comets could be rich in volatiles, carrying signatures of water and cyanide consistent with solar system analogues. That suggested interstellar formation environments were broadly similar to ours. Atlas disobeyed this lesson by presenting chemistry skewed so far towards CO2 that it contradicts those analogues. If Borisov's chemistry taught reassurance, Atlas's teaches disruption. The lesson of shared chemistry collapses. Even the broader lesson, that the first few interstellar visitors would define categories, has failed. Instead of convergence, the three objects diverge wildly. Oumuamua shows silence and unexplained motion. Borisov shows familiarity and normalcy. Atlas shows activity, anomalies, and contradictions. The lesson we thought we were learning was that interstellar objects could be categorized neatly into comets, asteroids, or fragments. Instead, the true lesson is that categories break when applied too soon. This collapse of lessons is not unique to astronomy. History shows that early discoveries often mislead. The first exoplanets suggested hot Jupiters were common, when in fact they were simply the easiest to detect. The first pulsars were thought unique, until thousands were found. The first quasars seemed inexplicable, until models of supermassive black holes emerged. In each case, early lessons proved temporary. Atlas continues this pattern, showing that the first few interstellar visitors cannot define the population. Their contradictions are not anomalies to be explained away. They are signals that diversity is broader than expected. For astronomers, this is both liberating and destabilizing. liberating because it frees us from premature closure, destabilizing because it denies the comfort of categories. We cannot apply lessons from Oumuamua and Borisov to Atlas without distortion. We cannot expect consistency across a sample of 3. Instead, we are forced to accept that interstellar objects may be as diverse as stars and planets, with no single narrative binding them. Each one must be studied on its own terms, without leaning too heavily on lessons from others. This realization shapes future priorities. If lessons from previous visitors do not apply, then each new discovery must be met with fresh eyes, not assumptions. Surveys must be prepared to detect the unexpected. Instruments must be flexible enough to capture anomalies. Models must be adaptable, ready to expand instead of enforce. The failure of lessons becomes an instruction in openness, a demand for humility. Speculation about artificiality also highlights the limits of previous lessons. Oumuamua invited it because of silence and acceleration. Borisov dismissed it because of natural behaviour. Atlas reopens it because of contradictions. The lesson we thought we learned, that artificiality could be set aside after Borisov, does not apply. Instead, the debate persists, showing that no single case can settle it. Each new object reintroduces the question, regardless of past conclusions. The broader truth is that Atlas is not only a comet, but a reminder that lessons often fail when applied too soon. Knowledge builds slowly, across large samples, through patterns that emerge only after diversity is revealed. With only 3 interstellar objects, the temptation to generalize is strong, but the failure of those generalizations is inevitable. Atlas embodies that failure. It shows us that the lessons of previous visitors do not apply, not because those lessons were wrong, but because they were incomplete. And so the study continues, with Atlas forcing astronomers to reset expectations. The lessons from Oumuamua and Borisov provide context but not rules. They shape questions but not answers. Atlas refuses to fit them, demanding recognition that each visitor will carry its own mysteries, its own anomalies, its own contradictions. Lessons may come, but only slowly, across decades of discoveries. Until then, Atlas stands as a reminder that the cosmos does not repeat itself neatly, and that certainty built too quickly is certainty built on sand. Every night of observation added something new to the record of 3-eye Atlas. Photometric curves grew longer, spectra grew deeper, astrometry grew sharper. The data flowed in from ground observatories and space telescopes alike, each dataset promising to peel away a layer of mystery. Normally in science, the accumulation of data narrows uncertainty. Anomalies shrink, probabilities converge, competing models resolve. But with Atlas, the opposite occurred. The more we measured, the less certain we became. Each new dataset that was supposed to clarify instead complicated. Each refinement of measurement sharpened contradictions instead of dissolving them. It became a paradox of knowledge. The curve of observation bent not toward clarity, but toward confusion. The paradox is visible first in chemistry. Initial spectra showed overwhelming CO2 activity with faint water signals. That was surprising, but at least it was an answer. More observations were supposed to confirm, refine, and contextualize. Instead, they fractured. Space-based infrared data reinforced CO2 dominance, but gave ratios inconsistent with ground-based observations. Photochemistry models suggested one balance, thermal models another. Adding more chemistry did not build a coherent picture, it splintered it. The more lines we measured, the less sure we became of which volatiles were truly present. Brightness followed the same path. Early measurements showed irregular variations. The answer seemed to be an unstable rotation or irregular activity. More monitoring should have teased out a period or at least constrained the variability, but each new set contradicted the last. Periods emerged, disappeared, re-emerged differently. Spikes in brightness correlated with dust activity in one dataset but not in another. The curve grew longer but no closer to resolution. The more we observed, the less we understood about how Atlas spun or vented. Trajectory illustrates the paradox in motion. Early astrometry left room for tiny deviations from gravity. More precise measurements erased them, suggesting no non-gravitational acceleration. Yet even those precise data sets could not align cleanly with activity levels implied by coma brightness. Instead of convergence, the paradox deepened. How could an object so active remain on such a clean gravitational path? Adding more data gave sharper numbers but no reconciliation. Precision made the contradiction louder. Size estimates show the same spiral. Initial guesses placed the nucleus anywhere between hundreds of meters and several kilometers. That uncertainty was large but expected. Infrared data, photometric modeling, and dust production estimates were supposed to narrow the range. They did not. Instead, they multiplied possibilities, with some pointing to a nucleus too small to survive interstellar travel, and others to one too large to explain suppressed water. The more methods applied, the wider the contradiction spread. Knowledge expanded, understanding shrank. Even the simple matter of classification fell into the paradox. From its activity, Atlas was clearly cometary. That was an answer, but its anomalies kept complicating the category. Too fast for typical comets, too CO2 rich for familiar chemistry, too contradictory for clear modelling. The more categories we applied, the less it fit. Labels became less useful as data grew. This paradox is not unique to Atlas, but amplified by it. In many fields, more knowledge reveals more complexity. Biology, geology, and physics have all faced periods where new data generated more questions than answers. But with Atlas, the effect is sharper because the opportunity is fleeting. We cannot keep observing until clarity emerges. The paradox is frozen in place, sealed into the record. The more we knew, the less we understood, and then the comet moved out of reach, carrying away the possibility of resolution. For astronomers, this forces a reckoning with method. Are contradictions failures of data or signs of deeper complexity? If contradictions persist, is the task to refine instruments or to expand models? Atlas forces the recognition that sometimes precision deepens mystery, because it exposes incompatibilities hidden at lower resolution. What seemed coherent when fuzzy becomes incoherent when sharp. The paradox of knowing more is that clarity can dissolve coherence. This paradox also reflects the scale of our assumptions. We assume interstellar objects can be modelled using solar system frameworks. The more data we collected, the more those frameworks failed. Atlas revealed not only its own complexity, but the inadequacy of our categories. Knowing more about it showed us less about its place in context, because the context itself was flawed. We thought more data would confirm universality. Instead, it exposed provincialism. Comparisons illustrate the paradox starkly. Oumuamua gave us little data but endless speculation. Borisov gave us rich data that fit comfortably into models. Atlas gave us abundant data that contradicted itself. It is the third scenario that reveals the paradox most clearly. Scarcity can breed speculation. Abundance can breed certainty. But abundance that multiplies contradictions breeds paradox. The more complete the picture, the more fractured it became. Speculation thrives in such environments. If more data generates more contradictions, then some turn to explanations outside conventional science. Artificiality resurfaces, not because evidence demands it, but because natural explanations fracture under weight of detail. The paradox invites speculation precisely because it denies closure. Knowledge expands, but understanding does not keep pace, leaving gaps that imagination fills. The paradox also reshapes expectations for the future. If Atlas could generate so many contradictions from so much data, then future visitors may do the same. We cannot assume more observations will yield more clarity. They may instead yield more paradoxes. Interstellar objects may not resolve categories, but dissolve them. The paradox may not be temporary but fundamental. The more we measure, the more complexity we uncover, and the less certainty we achieve. For scientists, this is humbling. It challenges the linear model of progress, where data accumulation equals understanding. Atlas shows that knowledge and understanding can diverge. We can know more numbers, more ratios, more trajectories, more brightness curves, and yet be further from comprehension. The paradox is not defeat but reality, a reminder that knowledge is not the same as wisdom, and measurement is not the same as meaning. As Atlas recedes, this paradox will remain its most enduring lesson. Its data will sit in archives, rich, abundant, contradictory. Future astronomers will revisit it with new models, new theories, new contexts. Perhaps understanding will eventually catch up. But in its own time, Atlas demonstrated the paradox of frontier science. Knowing more does not always mean understanding more. Sometimes it means seeing the depth of our ignorance more clearly. That is not failure, it is the beginning of growth. Every scientific investigation begins with the belief that enough time, data, and analysis will lead to understanding. It is the foundation of inquiry, the reason we build telescopes, launch missions, and refine theories. But 3, Atlas pushes against this assumption in ways that are difficult to ignore. Every attempt to explain its chemistry, its brightness, its motion, or its history runs into contradictions that do not dissolve. Answers create more questions, more data sharpens paradoxes, more analysis fractures consensus. The deeper we look, the less coherent the picture becomes. This raises a possibility that few scientists like to entertain. What if Atlas cannot be understood, not because we lack effort, but because understanding itself may be impossible? The suggestion is uncomfortable because it undermines the premise of science. Yet Atlas provides a case study in the limits of comprehension. Its anomalies are not isolated, not reducible to calibration error or missing data. They are woven through every property we try to measure. Its CO2 dominance contradicts our frameworks of cometary chemistry. Its lack of water emission defies solar heating models. Its irregular brightness resists rotation fits. Its dust production alternates between scarcity and excess. Its trajectory remains gravitationally pure when activity should disrupt it. Each of these could be explained alone, but together they form a web that no single model can hold. The contradictions may not resolve because they are not resolvable. This possibility leads to a deeper question. Are there objects in the universe whose complexity exceeds the capacity of human frameworks? Atlas might be one of them. Its origin may involve processes we cannot reconstruct, conditions we cannot sample, timescales we cannot grasp. Its chemistry may be shaped by interstellar radiation fields we do not yet model, or by formation environments entirely alien to our solar context. Its behaviour may reflect interactions of gas, dust, heat, and structure, too chaotic to predict or interpret. The universe is under no obligation to be comprehensible. If Atlas demonstrates that, it becomes a reminder of the limits built into our pursuit of knowledge. The impossibility of understanding does not mean the impossibility of learning. Atlas has taught us much, even if none of it resolves neatly. It has shown us that interstellar comets can be active in unexpected ways, that chemistry can vary radically, that brightness can refuse predictability, that trajectories can defy non-gravitational expectations. It has forced us to confront the fragility of assumptions, the inadequacy of categories, the insufficiency of early lessons. These are real insights, but they do not add up to understanding. They add up to awareness of ignorance. The final mystery is whether that awareness is as far as we can go. Consider the age paradox. If Atlas is billions of years old, it should be exhausted, its volatiles depleted. If it is young, its velocity should be lower. Both cannot be true, yet data supports both. We can describe the contradiction, but not resolve it. Consider the size paradox. If it is small, it should not have survived. If it is large, it should not suppress water. Both cannot be true, yet evidence supports both. Again, we can describe, but not resolve. The contradictions multiply until the act of description replaces the act of explanation. That is the edge of understanding. This recognition carries consequences for how science views itself. If Atlas resists comprehension, then it shows us that not every puzzle is meant to be solved in our time. Perhaps not at all. The cosmos may contain phenomena forever beyond the scope of human frameworks. That is not a defeat, but a reality. We can map what is possible to know and acknowledge what may remain unknowable. Atlas may sit on that boundary, reminding us that mystery is not an obstacle to science, but part of its fabric. Speculation thrives where understanding fails. If natural explanations fracture, artificial ones creep in. If contradictions resist closure, exotic scenarios take root. This is inevitable when mystery deepens, but the persistence of speculation itself proves the point. Without resolution, we fill the void with imagination. Atlas may never tell us whether it is natural or artificial, ancient or young, small or large. We may never decide because the data will never be enough. That is not failure, it is recognition of limits. The question then becomes how to live with such limits. Do we accept that Atlas will never be fully understood, or do we continue to pursue explanations in the hope that one day they will align? Both paths are valid. Science thrives on persistence, but it also requires humility. Atlas teaches that humility as forcefully as any object we have encountered. It reminds us that some mysteries may never collapse into clarity, and that the pursuit of knowledge must include space for permanent uncertainty. Comparisons reinforce the point. Oumuamua left us with silence and speculation, Borisov with reassurance, Atlas with contradiction. Of the three, Atlas may be the most important, not because it taught us what interstellar comets are, but because it taught us how little we may ever know about them. Its contradictions are not errors but messages, reminding us that comprehension is not guaranteed. The final mystery is not the comet itself, but the recognition that our frameworks may never capture it fully. This recognition extends beyond Atlas. It suggests that interstellar objects as a class may resist understanding, at least in early stages of study. Each one may carry contradictions born of origins we cannot reconstruct, processes we cannot model, distances we cannot trace. The paradox of knowing more and understanding less may be not an exception but a rule. The final mystery becomes not a question of this comet, but of the nature of science itself. What if there are limits we cannot cross? For astronomers, this is both daunting and liberating. Daunting because it denies closure, liberating because it frees us from the demand for it. We can collect data, archive it, analyze it, and accept that some answers will remain out of reach. That does not make the work meaningless. It makes it honest. Science is not only about solving mysteries, it is about mapping where solutions may never come. Atlas forces us to admit that openly. As Atlas recedes into darkness, it leaves behind not clarity but reflection. What if understanding is impossible? What if the contradictions are permanent? The mystery final, the enigma unsolvable? That is the question it leaves us with, the question that may define its legacy. The final mystery is not whether it is comet, fragment, or artifact. The final mystery is whether our desire for understanding can ever be met in full. Atlas does not answer. It leaves us with silence, contradiction, and humility. And perhaps that is the point. Not every mystery exists to be solved. Some exist to remind us of the boundaries of knowledge and to push us to explore those boundaries even when we know they may never collapse into certainty.